Sure, I'll kick you out. Then I'll turn it over to John. So thank you for day four. I think day one, two, and three went very well. So today we're definitely going to have really good presentations, and then after those presentations, uh, we're we're going to have a really good panel discussion with some of our presenters. So, Alicia, I will hand it back over to you to make some of the announcements, and then hopefully John can join us after that.
Awesome. Thank you, Preston, and good morning, everybody. Just wanted to give a couple of reminders specifically about your evaluation forms. So today wraps up our seminar, and we wanted to make sure and bring special attention to the instructions for block 18 and 19. Because you need to make sure and fill that out for each one. And then also, when you are completed your evaluations, please make sure and send them to christina.duran@associates.fema.dhs.gov. This email was also in your welcome letter. If for some reason you can't find your welcome letter or can't find this PowerPoint afterwards, you can also just email me directly, and then we will make sure it gets to the right place. Following the seminar, within 90 days, you will also get a separate survey that's sent out via EMI, and we do ask that you complete that as well. It's always great to have feedback. And then we want to just let everyone know that certificates will be emailed to the address that you use to register. And given the size of the group, we think it'll take about 15 days to process. And we did also want to, again, include all of the work locations. This goes into block 3 of your evaluation form. And I know throughout the last couple of days, some of you guys have asked about this. So we went ahead and included it in today's slide so you can refer back to it. And then just finally, a quick reminder to use the admin tech chat for any technical difficulties that you might be having, and the Q&A pod for questions directly related to the presentation and for the presenters. Again, if you are on VPN, we do recommend you disconnect for a better connection. We recommend the audio through Adobe Connect, but if you're having any issues with that, you can use the phone line. Please just remember to mute yourself. And with that, that completes our admin updates. And Preston, would you like to introduce our
The first speaker is Rick Scott, and he'll be talking about the Mackey Dam case history. So, Rick, the floor is yours.
Okay, can everybody hear me okay? I'll take that as a yes. We'll continue on. I appreciate this opportunity, and thanks to Preston. It was interesting when I saw the theme, risk-informed decision-making and benefit cost analysis. Well, that's what we're right in the middle of with Mackey Dam here. So I thought this was just a great fit for, even though we haven't completed it, we're in the middle, and I'll be going over some of the things that we've seen, and I'll get into it here. So also, I like the comment that Ignacio made yesterday at the beginning. He said, "We'll try to sound interesting." So I'll hopefully try to follow up with that and try to sound interesting as well, somewhat like Ignacio did. So I'm going to be talking. I'll just give you a little bit of introduction on the dam, our scope of work, those kinds of things, some of the challenges that we've been dealing with, and those aren't just with the dam. The issues aren't just dam safety related. There's other factors going into it as well. The qualitative risk analysis, which was less than what we had hoped for, and I'll talk a little bit about that. And then the next steps and kind of where we're at in the process. So going into the introduction on our scope of work, here's an aerial view of the dam. Our first task was development of a potential failure mode analysis. Originally, in our proposal, we wanted to do a quantitative risk analysis, but due to budget constraints, we scaled that back. And then we, from that, and this is where we're at right now, is on the conceptual level. So we're coming up with a 30% design with costs for our preferred alternatives to address the so conceptual design level. That's, we're looking at a 30% on the alternatives, and then we're going to go into the benefit cost analysis. And then when we proposed on this is our first experience with the benefit cost analysis, and probably, especially after listening to the presentations on Wednesday, I believe, I think we're in trouble there. So we'll have to be dealing with that as well. But we may have underestimated our level of effort on that. Then you have to have a public meeting, and then the application. This is an HMA, Hazard Mitigation Assistance Grant, and that's due, I believe, about the end of July for this particular project. So Mackey Dam is circled right here. Use the pointer, maybe. So that's Mackey Dam. Boise, Idaho is right here. Salt Lake City, Utah. I'm stationed out of, like I said, I work out of my home. I'm just north of Salt Lake. So the dam is actually in a pretty good location from our Boise folks and myself, that we can get there at about the same time. About 3-hour drive. So here's Utah for the geographically challenged, Wyoming, Idaho, etc. So that's about right where we're at. Here's a site plan of the dam. This spillway here was originally in the construction, and it's no longer there. The main spillway, the primary spillway, there is no emergency spillway on this. That's one of the problems we've run into. This is the primary spillway. Outlet Works towers right in here. Outlet Works release down into here. So the dam was built, it began in the early 1900s, and they started off with problems right away. And they actually suspended construction for 7 years because of seepage concerns, and I'll be talking a little bit more about that. It's just basically, it's a homogeneous sand and gravel, 1,400 feet, 7,200 or 72 feet high. The original design was 120 feet, and that's actually an important factor, because you always build, obviously when you build a dam, you start at the bottom and you work your way up. And so this bottom was constructed for the 120-foot high dam. So that results in a crest width now of 160 feet, because you've just basically truncated the top half of your dam. The dam itself, the reservoir is about 45,000 acre feet at full pull. Here's a section of the dam. We didn't have a lot of drawings either, and I just want to point out, it shows this core wall. This is not to scale, and this actually was an important factor when we went into our risk analysis, and so this is actually where it should be according to construction records. So it's actually higher than we first imagined or thought looking at the drawings, and it does only extend on the right side. And this is the dam as it sits now, with the original height showing here. So, and then later on they added this small berm here, and it's very difficult to even see on site. They haven't done real well with their maintenance on this dam. So the spillway and the outlet works, it's an uncontrolled overflow weir, not a large spillway, about 24 foot wide when it tapers down. The outlet works is an upstream control tower. with five 4x8 slide gates. And this is an interesting, this last bullet. Even back in the early days, it wasn't vandalism or terrorism. It was angry farmers, water users that wanted more water. So they took matters into their own hands and set off some dynamite. And it did survive that, but required some repairs. So we think of the troubling times in the days we have now, but this was nearly 100 years ago, 90 years ago when this happened. So not new. Here's the right abutment, and I'll show the, let's see, trying to find my pointer here. It's not working. Anyway, the Outlet Works tower is right here. This blue arrow is basically the tunnel for the Outlet Works. You can see where it discharges. You see, and this is the spillway inlet, the overflow weir right here. And you see a lot of vegetation right here, a lot of water. This is where they had all the seepage. And I'll be talking a little bit more about this, but significant seepage on this right side, and it is pretty closely related to the reservoir level. As it gets higher, seepage increases. But there are some things going for it that I know I'll talk more about that, but definitely lots of seepage in this dam. Here's a shot from the downstream side, looking over. So the right abutment, you can see it's been benched. That happened in the 80s. They had a lot of rockfall down into the spillway, so they cut that back, terraced it, and put in some benches. So that's helped with reducing the amount of rock they get into the spillway. Let's see. These are new pictures. I don't know what happened here. They look a little bit different than what I used to have. But this is, I apologize. I'm saying, what the heck are we looking at here? This is the seepage area on the downstream side, and I apologize. So I'll have to wing it on this piece here. But you can see the water. This is looking at the downstream. Lots of trees, and they've since removed some of those. And this is just looking from the right abutment, looking on the upstream side of the dam, the embankment. Here's a few more photos. This is looking at the spillway. It's pretty rough condition. There's a lot of spalling. This is looking at the downstream end. These walls are meant to be, there's a slight taper to them, but they're in bad shape too. And again, these are more photos of the Outlet Works tower. I'm hoping you can see this. I'm not sure how well you can, but they did do repairs in the 80s, and they had to dewater. And so I've never seen this live, but you can see these are the upper. There's 2 gates on the upper elevation and 3 on the lower. So challenges, issues, and deficiencies. A couple of them were just the limited funding availability and the inconsistent maintenance. The dam is regulated by the state of Idaho. There's no federal regulators on this dam, just purely for irrigation purposes. And they don't generate power, so they don't generate a lot of revenue off this dam. And maintenance is typically not been one of their priorities. And so there's definitely some issues there. And again, you can see on the right side here, that vegetation, those are big cottonwood trees. Should have been gone a long time ago. They're actually, since these photos are taken, they've started to remove some of those. But then there's the dam safety, you know, the failure mode issues, static, hydrologic, and seismic, and all of those come into play. It is in a high seismic area. There was a Bora Peak earthquake in 1983. It was only 25 miles from the epicenter from this dam, so it's fairly close. And I think they estimated the ground shaking at the dam to be about a 0.25 G, so pretty decent earthquake. It was about a 7.3 magnitude, I believe, on that earthquake. So, and then they had another earthquake just about a year ago that they felt at the dam too. So it is not immune to seismic loading. And then the spillway and the outlet works are the other issues that really started to we took a lot of notice of. So again, we went into the qualitative risk analysis, and that was a step back from what we wanted to do, but I think it still served its purpose. We were able to get quite a few folks to help us out with this. We used our own folks for the subject matter expert as much as possible. And then we also included Idaho Dam Safety and some federal folks from the Corps of Engineers, and there's Idaho National Laboratory, which is a fairly big. They've got reactors. It's just an energy producing place that's downstream of the dam. So they have a strong interest, and they would be impacted if the dam was to ever fail. So they had a person involved with that as well, and that was good. So we had a well-rounded team with lots of experience and lots of good input, lots of good ideas. So our goals on this was to identify and prioritize and categorize the most likely potential failure modes. And we because of the budget and the time, we focused on major issues only. So it was really these four things: the outlet works, the spillway, the right abutment, which has basically the seepage and the rock issues, and then the seepage and internal erosion that we thought, and I thought this would have been a more of an issue, but then it turned out to be there's really no evidence of internal erosion, even though there is significant seepage. And I'll talk a little bit more about that. So as always, you want to build the case, use facts and conditions, identify your adverse and positive factors and your rationale. When I say category, and I'll talk a little bit about that in a minute, but we basically went with the FERC categories that we've talked about already this week. Categories 1, 2, 3, and 4 it's even though this isn't a FERC project, it's good methodology and a good way to capture thoughts and identify where your priorities should be. And then identify the corrective actions, and that could be several different types of effort. It could be just monitoring and surveillance adjustments, operational changes, meaning maybe reservoir reductions or actual structural modifications. So that can be a wide range of options. And then our last goals, we definitely didn't want to have a reaction like this. Hopefully we keep everybody happy and not angry. So again, on the PFM, we did it FERC based, and it's just a tool, and it works. When I say just a tool, it's a good tool, and it's one we're familiar with, and it was applicable for this project. So I won't go over these in detail, but obviously the category 1s are the ones that are the greatest concern. Category 3 need more information. Usually, we tried to stay away from those as much as possible. And so we during this week time, it was a 5-day period. Actually, it was more like 4 days because we spent the first day and a half doing the site visit, just reviewing material that the district had, drawing reports and things. There wasn't a lot. It's an old dam without a lot of good data. So it was about a day and a half of doing that. So we had about a 3.5 day, really 3 day, because we left early on Friday. So pretty shortened session. And of that, we identified 4 category 4s, or 4 category 1s, excuse me, and 3 category 2 potential failure modes and 3 category 4 potential failure modes. And one thing I want to point out is these, when I first saw the dam and all the seepage, I thought these would be their main issue, but it really was not. Compared to the outlet works and the spillway issues and the inability to pass a major flood. So they actually, the tool system does work. The PFM system does work, and it does help you to identify where your greatest issues are. And this was a case of that. So I'm only going to just briefly go over the 4 category 1s. Those are the 4 categories that need attention. And this is just a summary. Due to time, I can't go over everything, but the outlet gates failed to operate during high flows. That was identified as a category 1. In facts and conditions, 2 of the gates are inoperable. So actually only in 1 gate only partially opens. So they don't even have full outlet work capacity at this time. And brackets sustain damage. They leak quite a bit too, even when they're all shut. The adverse factors, age and deterioration. Positive factors is relatively easy gate repairs, and you do have 5 gates. And then there were risk reduction measures, monitoring and surveillance were identified, but again, due to lack of time, we just don't have time to go into all that. So that's just kind of a brief summary. Here's a few photographs. This is, you can see some, this is whether it's a joint. But there's some cracking. They've done some repairs over here on there was a big void here that they filled with concrete. That was back in the 80s. These other 2 photos, this is actually the motor that they use to operate the gates, and it swivels around. This looks like a tire wheel for a truck, and it just swivels around. You can't really see it, but there's a horizontal rod that extends out, attaches to the gate. There's a couple of gates. The gates can also be operated manually with hand cranks if you got lots of time. So the next one was the Outlet Works Tower, and the pertinent features are damaged during strong seismic shaking. So the tower is definitely in need of repair. And it's the only means of supporting the gates, and therefore it's the only means of controlling releases from the reservoir, because the spillway is uncontrolled. It's just an overflow weir. There is noticeable concrete degradation and some horizontal offsets and some joints in the tower. And the positive factor did survive the 1983 earthquake, Bora earthquake, as well as that blast back in the 1930s. So, and again, for each failure mode, we had risk reduction measures, etc., identified. Here's a couple more shots of the tower. This is the top, so you come down these old stairs, and there's more stairs inside this box here, this shed. That grate right there is a vent that extends all the way to the bottom. So it's pretty old, not, and you can see on the right photo, you can see that those stairs that come down and kind of the little pathway there. This is also susceptible to rockfall, this whole area. And you can see at least one of the gates here, the upper gates. The other gates are submerged at this time. Spillway chute definitely had some issues. Fortunately, they've been able to, and it does operate almost every year, but they've been able to control their operations and limit the use of that spillway. And I'll show you a chart here in a few minutes, very interesting, that happened in 2017. But again, significant damage in the chute, lots of adverse and open joints, cracks, leaning walls, damaged concrete. It's likely under slab flows. There's no, the spillway is founded on bedrock. There's no underdrain system. But the quality, and there's been observations of flow leaks dissipating into some of the joints. Concrete is pretty suspect. Positive factors, they've been able to manage the spillway flows, even with 2.5 gate capacity. So they've been lucky, for sure. Let's see, did I skip one? Hang on. Okay, I'm just seeing where we're at. Okay, sorry about that. So here's just a few photos. This photo on the bottom left, that's about a 3-foot offset, and that is adverse, meaning the flow is pounding against it. So downstream on this would be on the top of the photo, and so that's not a good situation. And this is a shot of the spillway chute, looking from the crest. Pretty rough condition. Here's one of the spillway, just a shot of one of the walls, a section of wall. You can see a lot of seepage, weeping, calcite buildup, etc. And this one was overtopping the dam during an extreme flood event. And this is a serious problem as well. The PMF inflow is estimated to be about 82,000 CFS. Combined spillway and outlet works is about 10,000 CFS. And downstream flooding begins at 2,000 CFS. So as soon as they start releasing more than 2,000 CFS out of the dam, flooding occurs on roads and some infrastructure. So they don't, being able to pass an 82,000 CFS flood, and that's the inflow. So it would get attenuated somewhat by the reservoir, but being able to pass that would really not be the downstream population would still get flooded quite a bit. So we're looking at going with the FERC definition of an IDF, and that this dam should safely pass. And that's basically the inflow design flood, and that's based on incremental damage. So once you get up to a certain level, you've already done all the damage you're going to. So we've set that at 20,000 CFS. We don't have inundation mapping for this project, but so that's probably conservative. But so if you had 10 times the amount of when flooding actually starts to occur is a big part of the rationale there. So this one is and this is the maximum flooding that they had. This was in 2017, and unfortunately, everything kind of got messed up with so the arrows and the red circles don't match up to the drawing. So I'll just, hopefully you can see this the inflow is actually this jagged line here. Can you see my, I hope people can see my pointer. I can't get the pointer function to work anymore. But there's, if you focus on the bottom half of this 2000, where it says 2017, that's where the inflows came in, and there's 3 peaks. And if those had all been, if that had been one peak, they would have been in serious trouble. This is May. This first peak was in May. Second peak was first part of June. The third peak was the last part of June. And so they were able to manage, and their greatest flow that they had coming out was just a little over 2,000. So they were able to manage that without, again, using the spillway. The other thing to notice, this might be hard to tell, but this top line is the reservoir's elevation. And normally from February to May is when they're filling. But they take advantage of the snowtail, the weather reports, etc. They knew they had a flood coming in, so they did draw down the reservoir in preparation. And so they're not blind to the elements and the conditions that are out there. So they were lucky though, because again, these 3 peaks, if that had been one peak, they likely would have, well, they would have exceeded the capacity of their outlet works and had a lot of water going through their spillway, and likely would have resulted in damage. I think that's almost done here. So the next steps, we're working on conceptual designs and estimates right now. We're looking at doing some outlet works, tower refurbishment, spillway chute rehab, emergency spillway. Again, we want to be able to pass 20,000 CFS, not, which we determined to be a reasonable inflow design flood. And we have to be able to meet the district's repayment capability. That's a big piece of it too, because they just don't have, they've not set aside funding for future repairs, so they're going to have some issues to deal with there. So then we still have to do the benefit cost analysis, which I thought would be, I can do that in a week or two. And I'm afraid after listening to Wednesday's reports that we've underestimated that. But we're ahead of budget on the other pieces, so I'm hoping we're still okay. And then we've got the public meeting, let people know what's going on in the FEMA application, which is due at the end of July. And that is it. I think I'm on time.
For your presentation. It was very informative, and it looks like it'll be a great case study moving forward once rehabilitation is underway. We've got just about a moment, it seems like, for a question, and I see one here in the chat. If the risk assessment that you undertook, was that driven by the owners, or was there a regulatory push for this to kick off?
No, there was really no, like I said, the regulatory agency for this dam is the state of Idaho Dam Safety, and it's all part of the FEMA application process. So in the request for proposal, they did ask for some kind of risk assessment or an evaluation, and so that's what we propose. And again, we wanted to do a quantitative and really, spend the right time and get into it more. But with the budget we had, we just scaled it way back.
All right, great. Well, now that I'm back online, even though I was speaking to apparently nobody for a few minutes, and Preston jumped in to introduce me. So thank you for that, Preston. Let's. My watch says we're just about at 11:40, so let's move into the next presentation. And I see if any other questions come through, we can either answer them in the chat or save them for the panel later today. This next presentation is presented by a team from the RTI International, titled Portfolio Level Risk in Support of an Economic and Financial Analysis. This should be an interesting case study. So thank you for the presentation, and take it away.
Excellent. Can you guys hear us all right?
I hear you, John.
Excellent. All right. Thank you. All right. Good morning, everyone. Today we're going to be talking about portfolio level risk in support of an EFA, or an economic and financial analysis. And this is a World Bank case study, and we'll be focused on some of the tools and applications used for that case study, and then bring it to possible applications across the U.S. All right, as brief introductions here, I am Jonathan Klebman, Senior Engineer with in the Water Resources Center of RTI International. RTI is a nonprofit research institute based in North Carolina. I'm also with Sean Carney. He and I are based in Fort Collins with RTI, and then George Van Houtven as well. We'll be speaking later on some of the economic aspects. And Chris Wade also contributed to the presentation, but he is not speaking today. All right, so this is a case study that's really focused on the Dam Rehabilitation and Improvement Project, otherwise known as DRIP. And this is a World Bank loan to the government of India, with a target to improve the safety and operational performance of dams across India. It's an extension on top of DRIP 1. So DRIP 1 was started in 2012 to 2018, a 6-year program, about $500 million that included activities such as gate rehabilitations, stability, rock anchors, and stabilizations, etc. So it was a great success over that period of 6 years. And just recently, it was approved to move into DRIP 2 and 3, which is a 2-part project of 6 years each, with an overlapping 2-year period over 10 years. And it's about $713 million. Okay, so the dams across India, India has the 3rd most large dams in the world, according to ICOLD, with over 5,000 dams, with more than 400 dams that are under construction. And India is an extremely densely populated nation, and so they heavily rely on the dams and the infrastructure to support multiple benefits, including hydropower generation, flood control, and extensive irrigation across India. There's a number of initiatives underway to help support dam safety across India. In fact, there's a dam safety bill that is currently being passed. It's moving towards the upper house in India for passing. It'll be the first major national dam safety bill implemented across the country, because dams are certainly important critical infrastructure to support the nation. There's also a number of guidelines that are being developed by the Central Water Commission, which is a nationwide, under the Ministry of Water, including dam safety and risk analysis guidelines. And so dam safety is certainly a critical part of the program currently. For the World Bank project here, there's a number of key questions. The first one being simply, is this a viable loan? So the World Bank is, at the end of the day, they're a bank, and they provide money, they provide loans, and so they need to assess these loans to understand what's the value that is created from these. Is there sufficient value created from a dam safety program and dam rehabilitation activities to actually reduce risk to support a $700 million program over a number of years? And this is part of the EFA, which is the economic and financial analysis. And so the key question here is how can we use risk or look at risk to quantify some of the benefits, either through reduced risk or the increased benefits or reduced losses in the program under DRIP, and put that into an economic and financial analysis to assess the viability of this loan. And this is part of something called the project appraisal document. And so the appraisal document is the document that's prepared that assesses all aspects, environmental aspects, climate change aspects, etc., including the economic and financial aspects. And so here we're interested in developing unique risk-based approaches to assess the change in assess the changes that are implemented. So if you are replacing a spillway, if you are stabilizing an embankment, how does that change the risk profile, and what is the value associated to that? And so this is, as far as we know, the first time that there's been a risk-based approach that's been implemented within an EFA as part of a project appraisal document. All right, so we're going to give a brief overview of some of the components of risk. I'm going to pass it off to Sean Carney now.
All right, thanks, John. So yeah, as John said, we really feel this was a unique EFA in that it was risk-based. And so what do we mean by that, and how can we do a risk, do that when we have a limited budget? And we only, with this, we have a limited budget and about a couple, 2 months, 3 months to get this project completed. And so we can't get into the details looking across, a huge portfolio of dams, but we wanted to be able to use risk components or risk concepts to help inform the analysis of the benefits that are coming out of the improvement. And so let's get into just what the components of risk are. You guys are familiar with this from your work, but generally there's, if we're doing a typical risk analysis, like has been talked about, we would have a probable failure mode analysis where we're identifying what those major failure modes could be. We want to look at what the loading probabilities are, or the hazards, so either from seismic or flood loading or just general stability. And then given those loadings, what are the possibilities of having a failure that occurred with a certain amount of overtopping depth or a certain elevation during, how does that impact, what's the probability of a piping failure? And then ultimately, what are the consequences if there were a failure? What sort of economic or life loss consequences would there be? And then aggregate all that information together. So as the FEMA guidelines suggest, they take those 3 different pieces. And so we have the probability of loading, the probability of the failure given the loading, and then the consequences given a failure did occur. And so we take each of those pieces and aggregate those up together. And so we can take those, and for the purposes of this high-level screening, rapid screening analysis, we will look at each of these individually. So we have the hazards, so we can categorize those into 3 basic groups. So stability-related stuff that we'll talk through, seismic, earthquake-related failure modes, and then hydrologic failure modes. And then under each of those, there's a probability of failure given the load, and then the resulting consequences given that. So if we look into each of these, we'll start with the general stability. And so here we're talking about stability under different, or like the components that could lead to a failure mode due to general stability, such as tipping or sliding or piping failure. And so here we're really concerned about what is the typical operating range, and how does that vary through the year? If we're looking in January, maybe here's just a graphic, or just showing kind of the typical operating range in different months for a reservoir. And so from each of those, for a given month, we could translate that into what's the probability of being at a particular elevation, which may influence the risks due to piping. Then we can consider the seismic failure mode. And here in the United States, we're fortunate in that the USGS has this unified hazards tool that you can go to, and you can enter in your lat and long, and in a matter of seconds, get a graphic such as shown here that just relates the peak ground acceleration to the annual probability or annual exceedance probability of that peak ground acceleration. And so that's one indicator, one measure that would contribute to seismic failure. When we consider the case of India, there are different seismic zones throughout the country, and so we could use that information to help indicate where what the greatest hazards are for different dams as they're located in these different zones. But we don't have the same sort of benefit as we do in the United States, where we have a ground acceleration versus AAP. And so we need to make some assumptions related to that. When we consider the hydrologic hazards, this is a little bit unique from the others in that we're extrapolate. Well, I guess it's not unique. The probability of the quake is similar, but we're extrapolating from the observed record to the extremes. And so if we consider like the typical approach without considering risk would be to look at a PMF. Well, if we have a PMF estimate, such as we're showing here, where the PMF is higher than the top of the dam, that's a concern, obviously. And if the PMF would push the dam to that level, then we would say we need to address that. And absolutely, we need to address that. But the question is, what is the probability of that? And at what point do we overtop the top of the dam if we're getting a PMF like this case of about 108 versus 100? We're overtopping by 8 feet. Well, does that mean that it's we'll overtop the dam at a 10,000 year level or return frequency, or is it more like a million year? And so understanding that hydrologic loading is a challenge, and how do we extrapolate from the observed record, where maybe we haven't had any extremely large events, to those extremes? And so this is going to be one of the pieces that we spent a lot more time on trying to understand this, and John will get into some of the details on how we address that. So we've talked through the different hazards and how we classified that. So like if we think back to that original equation that we showed, we have the probability of loading, which is the hazards, so seismic or general stability or hydrologic loading. I think I said the three. But under each of those conditions, we need to think about what's the response of the different dams to that. And so in India, we had very limited information for this on this phase of the work. We had basic information about the location of dams and the dam type, whether it was a earthen embankment dam or a masonry concrete dam. We had the age of the dams and the time of their construction, what seismic zone they were in, and basic information such as the height of the dam and total storage capacity, that sort of thing. And so from that, we needed to come up with information on the system response probability. But as we all know, the site or what the issues are at a particular dam is really specific to that location, and it's really difficult to extrapolate that. So in this case, we really needed to make some pretty broad brush assumptions, and we had information on what the general state of the dams were, and so we could make assumptions on what those states would be, and whether it was categorize it basically on the probability of failure given that state. So whether it's in poor condition, moderate, good, or excellent condition. And similarly, we could say, okay, given the overtopping depth, if we consider the pre and post intervention, how the system response probabilities differ between those. And so one of the advantages, even though we didn't have the detailed information for each site, what we're really concerned about is thinking through how the interventions that would be done under the DRIP program, how those would affect the resulting risks. And so we could make assumptions about how a reservoir might move from a poor condition to a moderate condition, or with an overtopping depth. Okay, if they made improvements and had better reinforcement of the dam so the overtopping would not cause as much damage, all right, how does that shift the response probability? And using those assumptions, then we could assign values to those across the portfolio and use information from previous DRIP studies to see, okay, what sort of improvements were made and how could those be applied. So finally, with the third piece of that, we have the hazards, the fragility, and then the consequences. With the consequences, we can consider various different pieces here. So with consequences, you can do a breach, a dam breach, and then simulate the resulting flow downstream. And then from that, understand what the direct consequences would be, either from life loss or economic consequences. So both with structural losses or agricultural losses for agriculture that gets inundated and destroyed with a dam breach. But we can also consider the indirect economic consequences, and here we had information that George is going to talk about related to hydropower generation and irrigation losses and other aspects. So all these are important pieces to consider, and if there were a dam breach, would be a loss in India if that were to occur. So we need to, as we're thinking through the risks and what the benefit of providing this loan and making these improvements, we're thinking through each of these different components in terms of ultimately what the losses would be and whether the loan was beneficial. So now let's talk a little bit more specifically about the application of risk to the DRIP program, or the EFA analysis that we did. And so this just gives a real high-level overview of the components that we were working on. And so first there is just basic data collection of physical attributes of different dams and understanding what the hydrology is and gathering really a lot of global data sources that we were able to take advantage of for this analysis. The second component was considering the probability of hazards, and here we really were focused largely on the hydrologic hazards, and I'll get into why that is on the next slide. But also, you know, what is the probability of the seismic loading, and then for each of the reservoirs, what sort of pool levels are they at throughout the year that influences the static loading, which impacts those failure modes associated with more of a static loading, like the piping failures. Then we had to get into estimating the fragility and the probability of failure given the load. Again, given the information that we did have, that there were some real broad brush assumptions there, but based on information that was available. And then we're able to, with the consequences analysis, both consider direct impacts to dam breaches as well as indirect impacts to loss of fisheries or loss of agriculture and water supply. And finally, all this information, all the stuff to the left, was aggregated together into the economic analysis to look at what the expected benefits are with doing this loan, and then incorporating that into the project appraisal document. So there are a lot of challenges. Like I said earlier, we were trying to do this analysis in a very fast timeline. We had 2 or 3 months, I think, to complete the analysis, and we were looking across around 100 dams for this component, and so representative of the DRIP 2 analysis. And so we had limited data. That was probably one of the biggest pieces here. The historical records for reservoirs weren't available or very limited, and information about specific features such as a structures data set was not available, but we're able to use some global data sources that are available that have information on population and distribution of population across India, and structures and that, and then use some global precipitation data sources in that. There wasn't a lot of information related to the conditions. We didn't have the inspection reports and other standard stuff that you would have considering details at reservoirs here in the United States or elsewhere, or eventually with later moving down the road with the drip analysis. So we needed to make assumptions related to that. We didn't have information on the fragility and what the major failure modes were at different reservoirs. And so we were able to make, like we said, these conditional assumptions of, okay, given the reservoir is in poor condition, what sort of change would we expect pre and post improvements that are being applied, and what is a typical overtopping probability of failure and some of that. And finally, yeah, the interventions, we didn't have all of the information about what was going to be improved at every dam, but we were able to use DRIP 1 and the type of improvements that were done there as a proxy to what sort of interventions would be made in DRIP 2, and then assume the standard responses from that. So like I mentioned, we focused a lot on the hydrologic loading side of things, and why is that? First, there's information that we could use to help understand that more clearly than maybe some of the other detailed information at specific sites, but also just considering where the major issues have been over time. With the ASDSO has looked at the probability of failure, and overtopping is one of the highest things. If we take hydrologic loading plus like flood loading and lump kind of all those related failures, what instance there have been over time. Again, the ASDSO found hydrologic loading was one of the primary drivers in dam failures. And then finally, if we think about India itself, there was a study in 2013 that was looking at the inflow design floods for different reservoirs, and they've reassessed inflow design floods from what the original inflow design flood was used to construct the dam and what would be considered the inflow design flood now. And this is a scary graphic. On the x-axis there, you have the % increase in the design flood, and you can see there over half of those reservoirs, the inflow design flood is over 100% higher than the original that was used to design the flood. And so some of them up to, there's one, that far outlier there is approaching 100% or 1,000% larger. But there's a large block of those. Most of them are above 100% higher than what the inflow design flood was before. So it's recognized in India that hydrologic loading is one of the primary drivers and primary concerns. And so that's one of the reasons we focused there. And so, we, in the next little section here, I'm going to hand it back to John. He's going to talk through the tools that we had developed to help support the risk analysis and address these issues. So John, you want to?
Excellent. All right. Thank you, Sean. Yeah. So let's get into it here. In India, we're looking at the portfolio level, and we have nearly 100 dams that we wanted to assess to quantify some of the risk. And so this is an extensive amount of effort that is required, even at a screening level or a rapid assessment approach. It's still a lot of work. And as Sean mentioned, we had a very short budget and short time frame in order to accomplish this. And we focused on the DRIP 2 portfolio with a sample of 90 representative dams. And so using those to represent the broader project as a whole for the EFA assessment. But in order to do that effectively, we did need to create some tools. And so that's what we're going to cover here. One of the first things that we developed was an automated HEC-HMS model development. And so I think we're all familiar with HEC-GeoHMS, an application within ArcMap that can create the geometry files that are used for HEC-HMS modeling. What we did instead is we created an application that uses hydrocorrected DEMs to create a data set similar to NHD Plus for India. to create the basin topology. So we have the streams, we have the subbasins, et cetera, all created for the entire domain. We also used all dam locations, and so the dam locations are not just the dam of interest, but we're also interested in dams upstream that may have a regulating influence on the downstream dam of interest. And so those were also included and incorporated into the model development process. As Sean mentioned, we have the reservoir characteristics, so we're looking at volumes, we're looking at max spill capacity, and other important factors for the reservoirs themselves, which allows it to be parameterized. And then we have the soil data and the land cover data, and all of this is used to create a HEC-HMS basin file. And it's an individual basin file for each one of the dams. And so when we run through this process, we create nearly 100 basin files for the study area. And it's, again, parameterized using time area unit hydrographs and losses with green amped, and includes, as I mentioned, the regulated flows. So it's not just the dam of interest, but it's also other dams further upstream. So that was one tool that was developed. We also created an automated 2D HEC-RAS model development application so that we could start to look at some of the consequences. Using the base DEM, the SRTM data that covers India, again using the dam locations, looking in a downstream direction into the channel with roughnesses addressed using land cover. We're able to develop these models for each one of the subject dams automatically. The runs themselves include multiple hydrographs, and so we're able to not just run a static condition. Again, we're looking at risk, we're looking at probabilistic conditions, so we want the range of starting pool elevations that have different probabilities and different initial conditions. And so we're able to start from sunny day at some pool all the way through 100-year pre-channel floods downstream to look at the variations in the breach waves and the incremental impacts. The outputs themselves, again, being a fully 2D approach, result in the HDF files that allow us to look at the depth and velocities downstream. And then using some of the tools, we can automatically process that, and we can take those HDF files that have the depth and velocity, we can intersect it with a lot of the GIS data to extract the impacts. This is structural impacts, these are population at risk, these are agricultural impacts, etc. And so there's a lot of model runs, and so in this case, just as an example, if we have 100 dams with 5 scenarios per dam, we're looking at 500 HDF files. And so automating that to extract the information, do the intersections, and create the summary tables of the potential impacts is the post-processing application shown here. Within the US, there's, again, additional data sets that could be used. We have the National Structures Database. There's, well, OpenStreetMap is global, National Bridge Inventory, and other land cover data sets that can be used to help support the impact analysis here. So let's get into, as Sean mentioned, the hydrologic hazards was a focus. Again, we want to include, or we can include, the seismic and the structural conditions. Again, we're very data limited, whereas on the hydrologic side, we can use global data sets to develop a lot of this information and the estimates of the hydrologic hazard components. So the first component here is the precipitation. Within the U.S., we have Atlas 14, so we can grab the frequencies for various precipitation depths and durations and create curves. Within India, there is not an Atlas 14 process, and so we used global precipitation data, and so remotely sensed global precipitation to summarize the peak 48-hour events on an annual basis and develop these curves using L moments. So that was the first component. The second one is storm templates. And so given a precipitation event, and this certainly is applicable here in the US as well, you can get the frequency from Atlas 14, but you still need to know how to apply it and apply it spatially over your subbasins. And so using the remote sense data, we extracted the top 5 largest 48-hour events and use those as spatial and temporal patterns to apply the information that's sampled from the precipitation events to the watersheds. We're also interested in the storm seasonality. And so when do these events occur? And we can see here in India that there's a very strong monsoonal pattern extending from June all the way through October, when the peak maximum annual 48-hour events are likely to occur. And so we can use this information to sample randomly from and pull those initial conditions to know when the event is occurring, and use that to drive the sampling process. We can also include the initial snowpack. Again, if you sample a random month, we can then go to remote sense satellite data to estimate the snow water equivalent within your subbasins. This was certainly less of an issue in India, but the capability is there within the application to account for that. Again, using the temporal sequence, a random sample of when the event occurs, we can sample the initial reservoir levels. And so this would start the pools low or start the pools higher. And again, we can see that there's a general pattern in India of filling the pools through the monsoon season. So it starts low early Mayish, and they peak out at the end of the monsoon season. And so those will drive the starting pool levels for the sampling process used to develop the hydrologic hazards. And then soil moisture is a major driver of the influence on the hydrologic response. And so we use a random sampling remote sense data, which is a reanalysis product from ERA5 to develop the estimates of the initial soil moisture, and created CDFs of each of the watersheds. And so from those, by each month, we can sample randomly on the CDF, the cumulative distribution function, to look at the initial soil moisture content. And that's, again, used to set the initial conditions within the hydrologic model as we do the sampling process. And so these components also move us away from an AEP neutral approach, where a 100-year precipitation would be assumed to be a 100-year hydrologic response. And so here we can have a 100-year precipitation that produces a 50-year hydrologic response, or it could be a 300-year hydrologic response. And so this moves away from the AEP neutral approaches. The rating curves within HEC-HMS, it's not an operations model, and so we had to use static guide curves to guide the release pattern. And so using the initial pool levels, we fit a curve to the maximum release. This holds the starting pool at where we want to start, because the starting pool varies for each one of the samples that we developed during the sampling process. So each simulation has a custom rating curve that is applied into the HEC-HMS model. And all these pieces, we're talking about sampling as part of the PFHA, the probabilistic flood hazard analysis, which is a process of developing the hydrologic hazard AEP curves. And it runs through an algorithm here where we sample a set of storm depths and templates. And so we're able to draw a random sample, we draw a random month, and develop the precipitation pattern. And so that is sampled. We then sample again the feasible initial conditions, the snow water equivalent, the starting pool levels, the soil moisture, and this goes into a single hydrologic model simulation. We run that, and it develops the loading. And so we get a peak pool elevation within the downstream reservoir, our reservoir of interest, and then we repeat this process, and we do it thousands of times. So we're running thousands of HEC-HMS simulations per reservoir. And on the right side, we have the hydrologic hazard curve output. And so this results in the AEP curve for the hydrologic hazards, which provide an estimate of, oops. I hit the wrong button.
Yeah, let me pull the PowerPoint back up 1 second.
Yep, sorry about that.
No problem. It should open up to where we were, but we'll see what happens.
All right, sounds good. Don't hit the space bar. There we go. Excellent. Thank you so much. And so when we do that, it ends up with the AEP, which is very informative because it provides information like what is the estimate for overtopping. And here for this sample dam for reservoir 39, we can see we have a 100,000 year potential for overtopping. And so this is a direct output of this process. And I will also say that this algorithm and this process is developed and based on the RRFT application from the Army Corps of Engineers. And so using these tools, what were some of the results from the DRIP program? So from the hydrologic hazards side, we processed 90 dams in the end to use within the economic analysis. Each one of the dams was 1,000 simulations, so we did 90,000 HEC-HMS runs to develop the curves as shown here for a sample dam. So we had 90 different hydrologic hazard curves. And again, using an intelligent sampling approach, an efficient sampling approach, we're able to look at some of the rare frequencies, develop estimates of the AEP out to 1 in a million and beyond. And the development of the AEP curve here is a major step forward. I mean, this is a very valuable piece of information that moves us from a deterministic PMF approach into a full AEP curve at the hydrologic hazard, but also at the portfolio scale. And so this is very valuable information to assist in risk assessment. The hydraulic modeling side, using the HEC-RAS models, we're able to simulate multiple breaches per dam at different levels with 720 HEC-RAS simulations that were conducted. And here we just have a scatter plot that just shows some of the outputs, including population at risk and also some of the crop area that was impacted for each one of the simulations. And so tables of this information were used to drive the economic and financial analysis. From the risk analysis perspective here, there were a number of challenges. First off, in India, data is very protected. There's international restrictions in data, and data access is very challenging as compared to here in the United States using USGS information. And so there was no calibration, which is definitely a challenge. And so this certainly could be improved by getting site-specific information and using that. So this was definitely a screening level assessment across the portfolio. And again, as Sean mentioned, we're using generalized fragility curves. And so we're looking at pre and post project implementation to say this is an approximate intervention and here's the change. If you had site-specific information on conditions, on existing conditions, that would definitely be an improvement. But again, this is a screening level assessment to help guide the EFA process. The benefits include the expansion of the EFA techniques. So the possibility of including risk within the program here is a great demonstration, and it's definitely promising for future EFA studies. It is a screening level estimate at the portfolio scale. It is very rapid. We did this in a very short period of time with limited budget, and was directly used to support the World Bank within their EFA program. All right, so we're going to now move over to George Van Houten, and he is going to discuss some of the economic aspects and how this information was used.
Great. Thanks, John. Yeah, so the purpose of the economic analysis was to conduct a cost-benefit evaluation of the dam rehabilitation program in general and for the infrastructure investments involved. And both the costs and benefits were evaluated over a 25-year time horizon representing the minimum expected lifetime of the investment. And as with most infrastructure investments, the costs are relatively front-loaded compared to the benefits, and they're also relatively certain compared to the benefits. So starting with the costs, they were assumed to be comprised of 2 years of implementation costs to start with, so the cost of the structural improvements of the dams and things like that. And so that's where sort of the front loading comes in, because that was then followed by 23 years of assumed annual operation and maintenance costs, which were consistent throughout. For this project, the implementation costs were provided to us mostly by the bank, although in some cases we estimated them based on the size of the dam and other factors that we had. And the operation and maintenance costs were assumed to be just 5% of the implementation costs over that remaining 23-year period. So really most of the work, though, was focused on the benefit and the benefit estimation. I don't know, on my screen that equation isn't coming out at all, but the focus of the benefits, well, first of all, the benefits compared to the costs are going to be occurring farther in the future. So they'll start the year after the implementation is completed, so in the year 3 to 25. And it'll involve outcomes under uncertainty, so where the outcome, of course, is dam failure. And so we treat benefits as a probabilistic measure. So we're looking really at the expected benefits, so the probability weighted benefits into the future. And so that has two main components. So the probability component, which is the probability of failure for each of the modes, stability, seismic, and hydrologic. And that's, of course, what John and Sean were talking about and focusing on. For the economic analysis, we were really then focused on D, which are the damages, or the dollar value of the consequences of dam failure. And so what we're then looking at is estimating what those damages would be in each future year. So the model is assuming that the program is going to reduce the probability. So there's a delta probability that comes from the risk assessment, but that the actual magnitude of the damages, the conditional damages, conditional on failure, wouldn't be affected. Now that's a simplifying assumption. They could be, but really the action was going to be in the reduction in the probabilities. And so for each failure mode and each dam, we're looking at an estimate of what those damages would be, and then combining it with the reduction in probability, and then doing that for every year over the time horizon to get at the full profile of benefits and costs. And so with this information, we were then estimating 3 economic performance metrics in particular that are shown here, sort of the net present value. So that's essentially the difference between the overall benefits and costs of the project, but of course accounting for the timing of those benefits and costs and discounting benefits and costs more as they occur farther into the future. And I'll talk a little bit more about the discount rates that we use. We also calculated benefit cost ratio, which is essentially the same, but rather than taking the dollar difference, we're taking a ratio of the two. And then finally, an economic internal rate of return, which as the name suggests, is a rate of return for the investment, a percentage measure, which I'll also come back to talking about later. So we did this for each of the dams in the portfolio and then for the program as a whole. So in looking at these damages, we looked at 2 general categories. In a previous slide, they were referred to as sort of the direct damages and indirect damages. The direct damages are the flood damages for structures and for agriculture. And then I'll also talk about the indirect, which are the losses associated with the loss of reservoir storage in particular. So as John and Sean had mentioned, we were dealing with a fairly rapid turnaround, limited budget, data scarce environment. So we needed to make a number of simplifying assumptions along the way to simplify the analysis. And so, for example, with to estimate structural losses due to downstream flooding, we used GIS overlays to estimate the number of at-risk structures, overlaying inundation maps for the floods with structure flood footprint maps that we had, and then just simply applied an average value per structure based on government data from the government of India. So not really distinguishing between the size of different types of structures, but simply just taking an average value. So clearly quite a simplified approach for doing that. Similarly, for looking at agricultural losses, we're looking at downstream flooded areas. In this case, is overlaying with land use and land cover for croplands and the number of hectares of farmland that would be flooded in the flood events, and then applying a simple average per hectare agricultural revenue value with data at the district. So that would be like the county level not really distinguishing that much according to crops or specifics about the fields, but sort of a general estimate. And then as a sort of conservative, we multiply that by 50%, assuming that, of course, sort of depending on when the flood occurs, and that not necessarily all the crop revenue would be lost. And also that really what we would ideally like to be estimating here is a net revenue, also accounting for the cost of agricultural production and how those might be affected. But in any case, that was a simple sort of correction factor that we used. So those were how we dealt with those direct downstream flood damages. As far as the indirect, we looked at different categories. We also looked at agricultural losses, but in this case, losses associated with water use for irrigation from the reservoir. In this case, we acquired estimates of the irrigated area that was that used water from the reservoir. We didn't have specific data on exactly where those acres were. Presumably without irrigation water, that the revenues would be lost in those areas, but there might also be double counting with downstream flood area. So we made a simplifying assumption and reduced that by 50% to avoid that double counting. And again, use district level average values to get at the value per hectare, and assume that without irrigation, 90% of the revenue would be lost on those remaining acres. We also added in fishery losses. Now this is a relatively small part, but we did have some estimates about the average fish yield for each of the reservoirs per hectare. And so we multiply that by the reservoir size and rough estimates of the value of fish to get at an estimate of what those losses would be. But as I'll come back to in a moment, those were fairly small. And then finally, we were looking at hydropower losses. So only a subset of the dams have hydropower facilities, but we acquired information on historic rates of energy generation at these facilities, and assume that the revenues, these are the revenues that would be lost. We multiply the generation by an average price per unit, 6 rupees per kilowatt hour, so that's about 8 or 9 cents per kilowatt hour. And one of the things, and we've talked a little bit about the economic and financial analysis, and really the only difference for these World Bank projects in terms of economic and financial is really how costs are interpreted. For an economic analysis, we would be looking at what one would call a social cost. So the cost to society as a whole. So if there are external costs associated with a certain activity, those should be included in an economic analysis, whereas for a financial analysis, we would tend to focus simply on the private cost. So this is really where it made a difference, because if we lose hydropower, we don't just lose the electricity that's generated and the revenue from that, but we assume that they would need to be replaced by fossil fuel generation, which has externality costs in terms of carbon emissions. And so we included in that case what the cost, the global sort of damage social costs would be of those emissions as well for the economic analysis, but not in the financial analysis. And so quick overview of the main results. Most of the damages we'll see came from downstream flooding, and especially from structures. So in the pie chart on the right, although it may be difficult to see, about 62% of the damages were associated with downstream structures, and then 29% from agriculture. So really it's the downstream impacts that we found had the largest values. And then followed by hydropower, which is about 6%, and then lost irrigation, and then a very small part, as I mentioned before, being from the fisheries losses. And then taking those, we estimated those different performance metrics that I mentioned before. And so, for example, the benefit cost ratios, and depending on those vary, of course, depending on the discount rates that we use. And so using 10 and 12%, which are pretty high, is pretty conservative. So that's putting a pretty heavy down weight on future benefits. We still found that the ratio was greater than 1, so the benefits are greater than the costs. But as you go to a higher discount rate, the ratio goes down because you're downweighting those future benefits by more. And then so similar result with the net present value. It's a positive value. The benefits are greater than the cost, but with a higher discount rate, you're going to get a lower value for the overall net present value. And then finally, the internal rate of return. And one way of thinking about this internal rate of return is how high would we have to make the discount rate to push the net present value to 0 or the benefit cost ratio to 1. So as you can see, as you continue to raise the discount rate, if you raise it all the way up to 16.53%, that would drive the net present value to 0. So that's what kind of gives you an inherent economic internal rate of return for the project. And the financial rate of return really wasn't all that different because it only affected the hydropower revenues, and it was a fairly small part. As far as the limitations of the economic analysis, I mean, there were obviously, we needed to make a number of simplifying assumptions along the way, and we didn't have information about some things. So we did have estimates of loss of life, but we did not monetize those for the economic analysis. I mean, there's obviously issues or controversy surrounding whether and how you estimate life loss. It turns out for the analysis, in order to look at the benefits cost, we didn't really need it, so we didn't include it in the end. In terms of limitations, we didn't have data, detailed data on the value of downstream structures, so we're making a very strong simplifying assumption for those. We only had district level, we only used district level data on the per hectare crop revenues for this stage of the analysis. And there are a number of other, in particular, reservoir uses that we didn't include in this analysis. We've done in other analyses, and in DRIP 1 we did for specific dams, but for the full portfolio, we didn't look at, for example, losses in public water supply or industrial water users, or for example, recreational or other kinds of uses like that. We'd also, for example, didn't include avoided emergency response costs or things like that downstream. So it wasn't a complete set, but it's what we felt that we could estimate given the limitations. Other downstream things that we didn't include, for example, other infrastructure, right? We only looked at residential and other structures. We didn't look at roads and bridges and things like that. We didn't include damages to ecosystems and fisheries. So a number of ways in which the analysis could be expanded, a number of things that we could do if the analysis were done in the United States and we had more data. But that's where we left off with this. So anyway, let me turn it back then to John to talk a little bit more about the outcomes.
Excellent. Thank you, George. All right, so what are some of the outcomes? We went through the process. We described the development of the risk, some of the hydrologic hazards, and how it was integrated into the EFA process here. I grabbed a screenshot from Water and Power and Dam Construction back in December that shows, here the World Bank approves dam safety project in India, and so the pad was successful. The pad was completed, and the project is moving forward, which is excellent. That was back in December, and so we're very happy with that outcome of this process. But what is the relevance domestically? So let's think about moving some of these applications into the U.S. I just want to say, we developed a number of tools that we covered here: automated model development, the HEC HMS development, the 2D, the consequences processing, et cetera. And it's a very modular process. So for example, if you have an existing HEC RAS model that is already calibrated, already developed, that already includes a lot of the details of your downstream system, that can certainly be used. There's no reason that you have to use the 2D application that we've developed to generate those geometries. We want to use the best data available as possible. And so it can be as simple as deterministic modeling, developing a single HEC HMS AEP neutral approach to look at a given frequency event, all the way up through the PFHA. And so doing the stochastic sampling to look at the non-AEP neutral hydrologic hazard curves, et cetera. So it's a very flexible and modular approach based on what data is available or not available across the sector. Fortunately, in the U.S., we do have a lot more data that is available, and so it opens up a lot of opportunities to help support the dam risk assessments. The hydrologic hazards themselves can be used to help support an SQRA. If overtopping is a potential failure mode that's been identified, doing the hydrologic hazard can help identify what is the probability of the overtopping, and can be linked to it directly. So you do not need to go through and do a full, rapid screening level risk quantification, but instead you can use components of it to support the risk analysis or various aspects like SQRA. And this is an activity that we're helping to support the state of South Carolina in currently, and using some of these applications to develop these, as John McCain discussed earlier this week. And it's a complement to DSS-WISE. Again, if you need the hydrologic hazards, they can be used on one side, and if you already have the impacts from a DSS-WISE application for the consequences downstream, that information can be used together to help develop assessments of the risk at the portfolio level if those models are already existing. And I put a question mark here. We haven't done it before, but there's certainly extensions using some of the other OmniCore applications like FDA or using LifeSim to help look at some of the consequences downstream, again, using the outputs from the models that have been developed. With the HHPD program in particular is that there's a number of requirements for risk assessments under the HHPD program, and that includes that it needs to include static, hydrologic, and seismic conditions, and that's also within this framework. Again, we focused or discussed mainly on the hydrologic, but we are including static and seismic as well within the system. It needs to look at downstream consequences. We have the rapid assessment from the 2D breach analyses and also the intersection using automated GIS processing to look at the consequences. So that check mark is met. It needs to comply with the P1025 for screening level analyses, and so it certainly does that. It needs to be objective and reproducible. And so I think it's the transparency within this process is very high, and since we're using automated tools, it's a very consistent way of applying these across the portfolio. Right? Doesn't vary from site to site. It's equally applied to all the locations within the portfolio, and the information and calculations are all available to help support documenting of the process and looking at some of the outputs. So using these programs and some of these tools that have been developed for India are certainly applicable here in the U.S. and are actively being applied for some states such as South Carolina, and also North Carolina is using some of these components as well. So we'll stop there. Again, thank you for everyone's time. It's certainly an honor to be presenting with you guys, and we're really glad to have shared this information.
All right, thank you. That was a wonderful presentation and has inspired a bunch of great questions. One that I had initially is the grant from the World Bank to India. Is that then intended to be distributed kind of similar to the high hazard program from FEMA, where the government will distribute it to states or dam owners? And as a follow-up to that, or a piggyback, there was a question that asked if there's any policy or regulation type development assistance that's being part of this grant as well to support the dam safety law that was passed.
Yeah, let me start with the first part, which is it's not a grant, it's an actual loan. And so it is a loan to the government of India on the tune of $700 million that does need to be paid back. And so, and that's part of the requirement for the EFA, is if you go to the bank and ask for a loan to start a business, they're going to evaluate it and say this is high risk or low risk, and it's of sufficient value. And so that was part of the process. It's a loan with the government. With respect to supporting the dam safety program, through the DRIP program, there's definitely support for the policy. It's support for the regulations, the development of technical manuals and guidance for the program. There may be some future separate programs specific to the implementation and scaling of the dam safety law that is being passed. And some of it might fall under DRIP, and some of it might be under a separate separate program.
There was another question about the human life valuation. Is that something that India simply hasn't developed, or it's too complicated to include for your financial analysis?
Yeah, I'll start here, and I don't know if George wants to jump in after this, but you know, this is an active, certainly an active area of discussion. India is a very densely populated region, and you literally have millions of you know, lives, population at risk below dams. It's a challenge when you use our, you know, our standard risk forms. When you have 1 million lives, you could never reduce the hazard sufficiently with that level of population. So the scaling of it to the India context is a little bit challenged. And so you know, I think it's a matter of using good ALAR principles in following that and making the best decisions that are reasonable given the on-the-ground conditions in India. George, any follow-on with the value of the life loss?
Yeah, I would just add that there certainly are studies that have been done in India looking at the value of reduction in mortality risks that could be used to support that, and that have been in different meta-analyses. And for DRIP 1, when we were looking at those and looking at specific dams, we did pull information together for those. So there is valuation information that could be used, but of course, you know, these estimates are always subject to uncertainty and somewhat controversial. So, and I don't know about sort of specific government policies about the use of those values, but there is information.
George, maybe just to piggyback on that, like I think your comments in there was essentially like that would just show the value of doing the, like if we incorporated that as well, that would just further demonstrate that, yeah, this is a worthwhile loan to go after.
Right, exactly, and it would actually probably be pretty large, and so it would shift the calculus even farther in favor of the benefits in supporting the loan.
Okay. Well, thank you very much. There's a few other questions, but will you be available for the panel later this afternoon?
Be available for that. We'd love to address any questions, and also we can share our email addresses, and if you want to reach out, we'd be happy to discuss further.
Great. Well, this is so we'll start our next session. This one is titled the Rheindaler FERC Risk-Informed Decision-Making Pilot Project, presented by Dean Durkee of Gannett Fleming. Dean, take it away.
Okay. Thank you, John. Can you hear me okay?
Clear.
Very good. Thank you. All right. As John mentioned, I'm going to be talking about the Rheindaler Risk-Informed Decision-Making Pilot Project. I will go through an overview of Southern Cal Edison's risk assessment program, a little bit about the Rheindaler Dam, and then go through the results of semi-quantitative and quantitative risk analyses that have been performed, cover a little bit about some of the mitigation alternatives that we are considering, and then I'll touch on disproportionality and ALAR considerations going forward. So Southern Cal Edison was established in 1887, and they provide electric power to about 15 million people in Southern California. Part of that is hydropower, comes from, and there are 83 dams associated with that portfolio. And they produce about 1,200 megawatts of total capacity. Dams range in age from about 30 years old to 110 years old. And they implemented their risk assessment program in 2008, modeling that after Bureau of Reclamation's risk assessment program, dam safety and risk assessment program. So phase one of that was a portfolio screening analysis with the objectives of better defining their overall portfolio risk, improving their risk management, prioritizing some dam safety activities, and then of course justifying their budgets internally. These phase 1 workshops or portfolio screening workshops were conducted in 2009 and 2010, and they included folks from Southern Cal's Dam Safety Group, their project engineering and operations groups, and then they had consultants as subject matter experts, and FERC and the Division of Safety of Dams, State of California, also attended these workshops, plus some other dam owners as observers. And the results of those phase one portfolio screening workshops are shown here. Essentially, you've seen these types of risk matrices before. The different colored sticky notes essentially relate to different dams within the portfolio. Following that, there were some additional workshops to prioritize studies and actions to reduce and understand the risk that came out of those initial screening workshops. And there were multiple considerations in that process. For instance, what were they considered the FERC requirements, they considered the risk priority category, ease of accomplishment, or things that maybe some interim risk reduction measures that they could do at these various dams, some low-hanging fruit. And they wanted to build on the momentum of the work that was in progress. And then a focused review was performed on the higher priority dams. And at the end of all that, the Rheindollar Dam was selected out of that portfolio to take forward into the RIDM pilot project program. So a little bit about Rheindollar Dam. It's in the eastern Sierra Nevada mountains near the town of Lee Vining. And it forms Ellery Lake. You can see Rheindollar Dam here. And so just a little bit closer look at the Rheindollar Dam. It's a concrete-faced rockfill dam. It has a intake structure, the upstream side of the dam. There's a parapet wall that's been added since original construction. The valve house at the downstream toe. The auxiliary spillway shown here, and there's a flume downstream for measuring and monitoring flows through that emergency spillway. This is an older dam. There wasn't a lot of information available. A few drawings over, a plan view drawing, some details associated with the upstream facing. They have a section view that just shows that this was constructed out of loose rock fill, and then there was some effort during construction to place select fill on the upstream portion of the rock fill section, and then that was to prepare it to receive then the upstream slab. This just shows some details of the parapet wall that was added later. So the dam was originally constructed by Southern Sierra Power Company in 1924. In 1927, it was raised 7 feet. And then in the 70s, a remote control system was installed to control the center radial gate on the spillway. In 84, that remote control system failed during a storm event, and the gate failed to open. And all gates were subsequently locked into a raised position and ultimately removed by 1997. In 1998, they added parapet wall that included an extension around the right abutment. And then in 2006, FERC reclassified the dam as a high hazard dam. In 2008, there were some additional H&H studies that indicated that the spillway wouldn't pass the PMF. So some follow-up risk assessments were done in addition to what came out of the portfolio screening for Rheindollar Dam in 2015. And the objective was to evaluate any new information and review the prior assumptions at Rheindollar. And again, there were representatives from Southern Cal Edison's dam safety operations, and in addition, their licensing and law and risk enterprise management group. And then there were external participants from FERC and DSOD and other consultants, and they reviewed and updated the likelihood and consequence categories as needed for each of the failure modes that they had evaluated. Some of the key findings from that 2015 effort was that overtopping due to a flood event was the primary risk driver. The potential for spillway blockage significantly increases the risk, and almost all of the consequences are associated with a campground or seasonal campground downstream of the dam. Life loss for the sunny day failure was very close to zero. So then they took some risk reduction actions at Rheindaler Dam. They included, they had identified flooding at the spillway as a significant risk. So they removed the old radial gate frames. They raised the pedestrian bridge and removed the gate bay piers to allow for a single opening. And then they installed the log boom upstream and went ahead and applied for the FERC RIDM pilot project in 2016 following those interim risk reduction measures. So this is when we went into the semi-quantitative risk analysis, and we evaluated 8 PFMs associated with that included plugging of the spillway and subsequent overtopping. We had some other overtopping type scenarios and looked at stability as well as some seismic loading concerns. So that the SQRA was performed over 3 days in Bishop at the Hydro office in 2017. First day consisted of the team visiting the site and getting a good understanding of the upstream dams and reviewing available information and studies that have been developed previously. The second day was to review and update the potential failure modes, and then the SQRA was performed on credible PFMs on the third day. And the participants that time, this was a facilitated workshop with a facilitation team. We had subject matter experts for two H&H subject matter experts, a geotechnical subject matter expert, and a erodibility expert. And then there were participants from Southern Cal Edison's Dam Safety Group and Operations Group, and then the FERC regional engineer, and as well as FERC's Chief of Risk-Informed Decision-Making branch. And there were representatives from DSOD and an observer from another utility. So the results of that are shown here, and you can see that potential failure mode 1, which is spillway plugging during a flood leading to overtopping, was the highest risk failure mode to come out of that effort. A couple of others that were of concern, potential failure mode 5 was slope instability under flood loading, resulting in uncontrolled release, and number 8, spillway channel erosion due to flood discharge. So those were subsequently evaluated before going into QRA, and these were determined to be lower risk than they're portrayed on this risk matrix. So they were not carried forward into the quantitative risk analysis. So then in the quantitative risk analysis, we were really down to just this one potential failure mode, and this is how it came out of the semi-quantitative risk analysis. In the quantitative risk analysis, since we were going to be estimating nodal probabilities, we did some work to combine some of these nodes and economize a little bit and put them into a better format for estimating those nodal probabilities. So for instance, combining storm flood occurs in the basin, the reservoir begins to rise, and the flows occur in the spillway. That was considered to be one node in the QRA. We also looked at the potential for intervention. Of course, we looked at the reservoir rising above the parapet wall, and then overtopping flows exceeding the erodibility of the rock fill material, and we had some analysis to evaluate that node on its own. And then we looked at the structural stability of the slab under conditions of scour hole developing and exposing the underside of the slab. And so these were all combined into one node. The way that analysis was performed between the geotechnical structural engineer and the erodibility expert, it was possible to estimate that as one node. And then we looked at continued erosion leading to successive failure of the slab and breach of the dam. So this is just one leg of that event tree, or one branch of the event tree, and this shows the revised potential failure mode that was taken into the QRA. So for each one of these, we had different ways to evaluate or estimate the nodal probability. So for the flood event, we had a stochastic event flood model that was developed and flood frequency curves. We considered the general storm as well as the local storm for this, and we looked at this with debris blockage as well as without debris blockage. And you can see the range here for both of those cases. And that is the return period. What you're looking at is the return period that would that would overtop the dam. So you can also see these flood frequency curves here, and this shows the elevation of the parapet wall and when we start to overtop the dam, somewhere between a 10 to the minus 3 and 10 to the minus 4 annual exceeding probability. We looked at structural intervention to prevent overtopping of the embankment, and we considered this through just expert elicitation and discussion, considering the time of failure versus notification and action. This is a relatively remote site. The resources are pretty limited at the site in order to respond to something like this. And the location of the first responder would be in Bishop, an hour away, and there would be a delay in notification and then that person having to travel to the site. So we felt that there was a high probability that we can't intervene, and if successful intervention were to occur for flow in the groin area, which I'll explain in some later slides, the overtopping would shift then to the rest of the embankment and not substantially lower the risk. So then with regard to the parapet wall overtopping, again, we went back to our flood frequency curves to consider that. And then the conditions exist that allow erosion to initiate. We considered that both at the groin location, and you can see that here, where flows would be concentrated, and it was likely that erosion would initiate sooner in this location. And we also considered erosion over the main part of the embankment. And then erosion leads to failure of the upper portion of the concrete slab. So there was an erodibility analysis performed by Mike George in this case. Erosion is likely to be most significant along the groin just due to the concentration of flows, as I mentioned. Failure of the slab is likely to occur when the exposed height is at about 3.5 or 4 feet. So this was just a structural analysis of an unsupported section of the slab due to scour hole developing beneath it. Potential for initial slab failure increases significantly at overtopping flows greater than 2 to 4 inches. Could also occur at 1 to 3 inches if the storm duration is longer. So we looked at both considerations, both the depth of overtopping and the duration of the storm. Failure also possible anywhere on the embankment at 5 to 7 inches of overtopping. And although the general storm is significantly longer than the local storm, the time from onset of overtopping to failure is pretty short, on the order of 0.25 to 3 hours. And again, we consider intervention to be unlikely. So this just shows the results of the erodibility analysis. You can see the probability or likelihood of initial concrete slab failure plotted as a function of the depth of overtopping and also related to the storm duration exceedance probability. We looked at this both for the typical embankment section and within the groin section. So the results shown in green indicate that there's no or insignificant erosion. The yellow is that erosion could occur, but the slab would not be exposed. Orange was where we estimated that the slab is exposed, and of course the red, the slab is exposed and likely to fail. And then we looked at continued erosion leading to successive failure of the concrete slab and eventual breach of the embankment, essentially just through discussion and expert elicitation. For the consequence estimate, there was a 2D dam break model developed, and then we used the RSIM method to evaluate potential life loss. And one important part of this is that nearly all the population at risk, again, is in a campground. And when you look at these, about 90% of these local storms occur between May and September, which is the peak recreation season. And about 90% of the general storms occur between November and March when the campgrounds are closed. And you see that in the results. There's much lower potential life loss in the off-season. And then we looked at the shoulder months as well as the peak season as it relates to the local PMF. So life loss here it ranges from less than 1 in the off-season to close to 10 in the peak season. So for the quantitative risk analysis, we estimated nodal probabilities, and we did that through the appropriate SMEs, depending on the particular node and the failure mode, in the failure mode. They were asked for low and high estimates first to avoid anchoring the range to the best estimate initially. The probability distribution function discussed by the group was discussed by the group and then used in a Monte Carlo simulation, and the annual probability of failure was established using the at-risk model. The distribution of the annual probability of failure was developed based on a range of probabilities for each node, and then the consequence analysis was performed using Monte Carlo simulation to develop a range of potential life loss. And then, of course, the annualized life loss was generated using the likelihood that came out of that and the potential life loss. And so this shows the results for the general storm and the local storm. And then using a weighted average approach, we estimated the overall annualized probability of failure and incremental life loss, estimated the risk that way. So that was just a quick overview of the semi-quantitative and quantitative risk analysis. And then we held a subsequent meeting to look at what our mitigation alternatives were. And we had two approaches to these structural mitigation alternatives. One is to lower the probability of overtopping, which we could do by adding, for instance, an auxiliary spillway, modifying existing spillway, or modifying the parapet wall. We could also provide overtopping protection or armoring of the rockfill using a roller compacted concrete, articulated concrete blocks, and boulders and boulder type of riprap. So just looking at lowering the probability of overtopping, we looked at adding an auxiliary labyrinth spillway, for instance. This is just an example of one way to do that. You could also increase your spillway capacity at the current location of the spillway by modifying that, replacing the existing overflow section with a labyrinth spillway. We could also replace that with a longer OG crest. Another option is to raise a portion of the parapet wall, which you see in yellow, and then lower the remaining portion of the parapet wall, which you see in blue. This would just give you more spillway capacity on the left-hand side of the dam. And that would require you raise the existing parapet wall like you see here, and then on the remaining part of the dam, you would probably want to armor the rockfill in that area. That's going to be part of their primary overflow section, so it might look something like that. So we then went back and evaluated these options just based on a general increase in spillway capacity, so lowering the annual exceedance probability, understanding that these are conceptual at this point, but in design we could develop them to target any annual exceedance probability that we wanted. So based on that information, we looked at how that would change the overtopping flows, the depth of flow, and so on, and then reevaluated the nodes within that failure mode or that event tree going forward. to re-estimate the risk based on that new condition. And you can see the results here for both the general storm as well as the local storm, and then again, the overall annual exceedance, annual probability of failure. So overtopping protection alternatives, again, I mentioned the RCC as one option. That might look something like you see here. We did not go back and re-estimate the risk for these. We felt that these could be constructed in a robust fashion and significantly lower the risk overall, depending on with any of these options. So this just shows the articulated concrete block armoring option. This is an example of what that might look like. And then at this location, there are a large number of, there's a significant number of large boulders in the immediate area of the dam. You can see that here. The dam is shown right here in this photograph. You can see the spillway on the left. And a lot of this material could be used to build a boulder type armoring on the downstream face or extend a buttress off of the downstream slope of the dam. And so you just selectively pick those and place them where you needed them. You could also slush grout that boulder fill and provide significant erosion protection. This is what that might look like. So we developed some conceptual construction costs associated with each of these alternatives. We looked at what the range of cost might be, and then those were used later in the disproportionality calculations. So then non-structural alternatives also include enhanced warning system. With the low population downstream, it's possible that a warning system could reduce the risk significantly. We talked about the option of moving the campgrounds. That would be challenging, but not impossible. It would take significant coordination with U.S. Forest Service. So for disproportionality, we considered the range of costs for structural alternatives, the range of costs for non-structural alternatives, and then we looked at other annual costs associated with those and considered the mitigation effectiveness of those, and then the annual lives saved. And so then calculating the disproportionality, technically if you go by FERC's guidelines, this is considered poor disproportionality, but we're in the early stages of this, and there are maybe some other things that we could do to refine these costs and show better numbers, but they're not completely out of the question in terms of disproportionality and supporting the project going forward. So going forward, we're going to be considering ALARP, and that's going to take into consideration cost effectiveness of the project, the risk with respect to the tolerable risk line and with respect to individual risk, relevant good practice, both from FERC, DSOD's consideration, and Southern Cal Edison's concerns, and then the community concerns. Downstream property is highly valued in this area. It's prime camping area, and it's used quite extensively during the on-season. So just summarizing, the phase one risk analysis was performed in 2008. This was the portfolio screening. The focused risk review was done at follow-up to that, and Rheindaler was selected for the RITM pilot project. A level 3 semi-quantitative risk analysis was performed in 2017, and 3 candidate PFMs were selected for QRA. The supplemental investigations following the SQRA eliminated those 2 PFMs from further consideration, and then additional analyses were completed incremental to track with the level of risk analysis throughout this process. And then one other observation here was that initiation of the failure modes based on the overtopping depth worked really well for considering spillway modifications, and it made it quite simple to go through that process. So thank you for your attention, and I think we probably have a little bit of time if there are any questions.
Thanks, Dean. We do have a few questions here. The first one is, I'm going to combine a few of them here, talking about the parapet wall. some folks are curious about the consistency of the top elevation, if there's any areas that would overtop sooner. And following on to that, there was another question regarding the idea of periodic surveys of the crests of the dam, and I suppose the parapet wall as well, and how that might pertain to TFM1 and the overtopping risk.
With regard to the consistency of the crest, the dam crest is surveyed on I don't know what the exact interval is, but there is an interval where it has to be surveyed periodically as part of the FERC and DSOD's requirements. But there was a low spot identified on the right abutment contact area a number of years ago. And when we were in the field during our initial site visit, that question came up, and it was subsequently surveyed and determined that that was not a low spot. So if there are other low spots along that parapet wall, those were not considered to be significant during our discussions in these workshops. There could be concentrated flows in some areas, so I think that's what this question is driving at, and that would definitely affect our estimates of erodibility, where you would get an impinging jet onto the rock fill and more rapid erosion. And then the subsequent question are periodic positional surveys of the crest performed, and like I said, I believe that they are. I can see the questions, John, if you want me to just respond to them.
You may feel free. Yes, go ahead.
So there is a question, did FERC regulations require you to use RSIM for life loss? No, they didn't, and in fact, there was discussion about whether or not to use the LifeSim model. We looked at how much value we would get out of that with the relatively low potential life loss, and decided not to go down that path. We did, Southern Cal Edison performed those analyses themselves, and they did do some preliminary LifeSim estimates, but they weren't getting really a significant difference in the results. And then there was a risk review board convened as part of this process, and the considerations for changing the downstream conditions, and so that we could alert people faster and lower the consequences that way was a big part of that discussion, and so that's something that's still under consideration at Southern Cal Edison. Looks like there's another question: were geotextiles considered for overtopping protection? If not, what was the reasoning? No, we really didn't consider geotextiles, primarily because it's a material that we would have to import to the site, and with the rock fill that's there, it's probably cheaper to use that than the geotextiles. And we've also, I don't know how DSOD and FERC feel about the geotextiles in that type of application, but it is something that we could certainly consider. Let's see, looks like how it was justified to proceed with QRA after SQRA identified the sole risk driver of inadequate spill capacity. So yeah, it's a good question. I've given this presentation or parts of this presentation before, and that's come up. I think Southern Cal Edison had a pretty good idea of which direction they were going to go with this even before the QRA. But the idea was to run this through the pilot program, FERC's pilot program, and it was a relatively straightforward one compared to how complex these QRAs can get. And so Southern Cal Edison opted to go ahead with the QRA to work all the way through the process of the RITM program. I don't see any other questions in the chat. So thanks very much. And if there are questions afterward, I plan to sit in on the panel session.
Great. Thanks so much, Dean. Great presentation. And just a reminder for everybody to send your evaluations, discussions about future topics, and things like that to Christina Duran. Email address is in the notes panel on your screen. Make sure we get those in from everybody. We are a few minutes ahead of schedule, but I think we can move to the next presentation now and provide an opportunity for some flexibility in the schedule if needed as we move throughout the day. So the next presentation we have is titled Risk-Informed Decision-Making and Asset Management of Critical Infrastructures. Presentation will be given by Dragan Komljenovic. I'm sorry, I tried to write it out as a phonetic spelling, Dragan, and I still got tongue-tied. I apologize, but you represent Hydro-Quebec. So thank you very much for offering to present today, and the floor is yours.
So I could start. In fact, I am not a safety guy, dam safety guy, and I discussed with organizers, and what I am going to present is my experience in using risk-informed decision-making as a former nuclear safety and reliability guy, and right now in transmission business. So in the larger scope of asset management. So I saw a lot of great presentations, so I hope I will be up to task to do that in my case. So it is my presentation outline with some introduction asset management and models and some case studies where we use the risk-informed decision-making with some concluding remarks. Some numbers about the Hydro-Quebec. It is one of largest electrical power utilities in North America with almost 25,000 people and 4.4 million customers, generation capacity almost over 37 gigawatts. And transmission grid is over almost 35,000 kilometers, where over 12,735 kilovolt, with 554 transmission substations, 15 strategic interconnections with neighbor grids, Canada and US. Distribution grid is medium voltage, almost 120,000, and also low voltage. So what is particular with Hydro-Quebec's grid is that main production units are far in north and main consumption centers are far in south. So we have over 1,000 kilometers of transmission lines through harsh climate conditions, and it is quite challenging to provide the reliability of service. So it is Hydro-Quebec. But why I start with asset management? It is to establish a larger and appropriate context and framework for risk-informed decision-making. It is, in fact, important to understand forest and trees, you know, the detail, the micro level and macro level, and to provide a holistic view of the overall environment where the risk-informed and asset management should be integrated. At this regard, look at the critical infrastructure is important, important in asset management and risk-informed decision-making. What I captured this talks from John Woodhouse, who is an expert in asset management. He said that decision-making is not just the technical process and modeling and that issues. It is also about human psychology and dimension. And at the end of the day, it could be a dominant factor in decision. So in some in following slides, we are going to see some illustration of that. In the overall context and critical national infrastructures, we could say that the infrastructures are capital-intensive organizations and very complex in terms of their internal structure, operations, and technologies used. And they are also exposed to deep aleatory and epistemic uncertainties and composed on many independent systems. And this complexity is not always understood and controlled. So in this regard, we could see some system-level breakdowns, given that those systems are fragile. And such system-level breakdown may consist of physical damages and destruction of physical assets, natural disasters, weather phenomena, human actions, and so on, or functional disruptions due to with no physical damages. For example, pandemics we are right now in. So we see that those factors are basically external to organization, and we have to cope with that, and we have to model that. And the experience has shown that traditional methods are not necessarily good enough to capture that. So we have to think, plan, and prepare differently in coping with these challenges and remain economically viable. So, critical infrastructures, just recall that electrical power grids, communication grids, large dams, all those systems we use in everyday's life, and they are also the part of high reliability organizations. So, and they also operate in increasingly complex environment and given to market evolution, budget restrictions, new technologies, climate change, and so on and so on. So in this regard, high impact, low frequency events are significant factors in decision making. Some characteristics of contemporary critical national infrastructures: hypercomplexity, tight coupling, extreme differentiation in hierarchy, large numbers of decision makers and various levels, compressed time factors, and complexity of operation, as well as inability to withdraw or modify operation decisions. As an example, from this OECD book, it is an example of interconnection between electrical power grids and other critical functions in the society. The assets in infrastructure are complex, highly interdependent, and their behavior is quite emergent. So they are very expensive, large quantity, exposed to harsh climate conditions. Remaining useful life is not easy to estimate, high consequent failure, and so on and so on. We all know that, and it is important to keep in mind. So various organizations owning those infrastructures are also challenged with the end of useful lives or the obsolescence of those structures. So we have to upgrade that to grow capacity. So in this context, we have to get the right tools to support decision-making process and keep required levels of performance. So in developing those approaches, we have to take into account huge uncertainties and the interconnections between elements and systems that we have to take into consideration: physical energy, material information, and so on, type of lengths, and various time and spatial scales. So we have to keep in mind that we should take into account that there are extreme and surprising events which are the result of complexity and opacity of those systems. So in this regard, the concepts of resilience and structured engineering asset management put together might provide some efficient frameworks for coping with this complexity and help managing critical infrastructures. The resilience, it is only a short recall that we have several phases in those resilience cycle with normal operation, adverse event occurrence and absorption phase, and various recovery paths, and post-recovery with the various levels of performance depending on the type of event. What is important to stress that we have several types of environments, internal environment with technical systems, we control that really well. Internal organization where we could strongly influence, and all that external environment we don't control but we are exposed to. And the resilience management is there, and the operational and asset management is in lower levels. So the resilience management includes operation management, asset management, system and engineering design, research development, various general excellence in management, risk management, but also a legal and regulatory framework. It's a cumulative effect of those yields the result that are superior to individual results. In this context, asset management, some basic principles is what does asset management mean is for various people it is various definition, but for us we could go to the ISO 55 series of asset management standards, so where the definition is coordinated activities of an organization to realize value from assets, and asset is an item, thing or entity which has a potential value to organization. They could be tangible, financial or not. So in this standard, human resources also considered as assets. The efficient organizations use this approach of asset management to resolve competing priorities to ensure long-term benefits, and helps the asset management system helps an organization to establish a coherent approach and coordinate the delivery of resources and activities. What is important to say that the asset management doesn't focus on the asset itself, but it is business purpose centric, and it is in fact the philosophy to the way of doing business, and focuses on total business experience. In fact, it helps you responding the question where to spend your first or last dollar. Some benefits, you could see that better managing of risk, demonstrated social responsibility, enhanced reputation, improved financial performance, and so on and so on. So you could find that in mentioned standards. As far as selected asset management models, it is basically to balance the cost, the risk, and the performance. And you have the risk of failure, which is increasing with changing maintenance cycle, and the cost of preventive activities where we have an optimum. It is the approach by the Institute of Asset Management. And the overall, the structure of asset management is we have 6 groups and 39 subjects of importance, and decision making is as a part of these 6 groups. And in this part, we have developed risk-informed decision making in asset management. I am going to speak a little bit later. Given that I came from nuclear power industry, this industry has developed in the past so-called risk-informed asset management, in fact, at the end of the day, you have the maximize your profit or minimize your cost with revenue model, cost model, safety model, generation, and so on and so on. For electrical power utilities, it is a similar approach. You have the maximize the value, minimize the cost. We have the revenue model, cost model, delivered power, reliability, quality, and so on, so that you have all those factors in mind to make sure that your decision making is optimized. And as far as the confidence in models and results of those models is concerned, I put some of my exchanges with Peter J. from Woodhouse Partnership, which is the member of technical committee, ISO technical committee in charge of ISO 55000, where it is, I like that he said that I am particularly nervous of techniques where people put numbers into a model and accept the answer without understanding how the model works. So it is particularly important for young people who start in the profession, that knowing that they have to develop good models, but also to be aware of the limit of the models. So the decision making as a part of overall asset management, it's the types of decision is capital investment, operation maintenance, shutdown and outage strategies, life cycle value realization, resourcing strategy, and so on. So we have to put that to find out the optimum on all those competing factors. So in general, we have to maximize asset value, to take into account safety, reliability, life expectancy, capital cost, operating, environmental, regulatory constraint, but also we have to take or not to underestimate the shine factors, public image, customer impression, the quality. And in this regard, risk-informed decision-making, such as I like this definition from the Canadian Nuclear Power Standard, is a process that provides formalized, rational, and systematic methodology for identifying, assessing, and communicating various factors that support decision making a risk-informed decision. And there is also some models. I am going to present you the model we developed at the Hydro-Quebec Research Institute, where the risk-informed involves considering appropriately weighting and integrating a range of complex inputs, often very complex. What are those inputs? It is from traditional engineering analysis, deterministic and probabilistic analysis, operational experience, cost-benefit consideration, regulatory requirements, also allowable time at risk, the allowed duration to exposure to risk, and any other relevant qualitative or quantitative influence factors. And it is important to stress that risk-informed decision-making is not replacing a risk management process, but rather supporting that. And it should be the part of overall management of the system. So you have had a quite interesting reference in NASA, use that. It is the Canadian standard. It is also U.S. Nuclear Regulatory Commission produced a lot of very interesting regulatory documents. You could also download MIT PhD thesis, which is International Atomic Energy Agency, and so on. It's a lot of, and the FERC also produced some guidelines. So there is a lot of interesting references in this field. As far as our approach, our model is concerned, it is basically divided in three major steps. The first one is establish decision-making context. The second step is perform detailed analysis, engineering, risk, economic, and so on. And the third step is deliberation and decision making. So, who are the participants in the whole process? Analysts, the individual organization which applies the methods, subject matter experts, the individuals or organization that have a particular knowledge upon the problem analyzed, decision maker, individuals who have the ultimate responsibility to make decision, management, stakeholders, and decision maker can be also a stakeholder. In this regard, the first step is more detailed. You could see that I am not going to explain every single step inside, but what is important that in the first step, and we should not underestimate the effort for the step. What is the problem? What is the context? The stakeholders? What are the options to be considered? Decision to be made? Methodologies to be used? And any other relevant elements. So in the second step, in the first step, it is basically performed by management, decision makers, and subject matter experts. The second step is really the detailed engineering, reliability, and so on analysis, and it is basically performed by analysts and subject matter experts. And this stage produces results, insight, and formulate recommendation to decision maker. The third step belongs to decision maker and involves deliberation and final decision making and communication. So what is important that the subject matter experts and analysts provide relevant information, and after a series of deliberation, the decision maker can make his or her decision. What is important to stress is that it is deliberation do not demilitarize the use of importance of scientific and technical understanding of the problem, but it is to take into account a broader context. And after deliberation, the final decision is made. And the organization has to provide necessary resources and implement decisions. So decision makers are informed. To illustrate this methodology, I am going to present two case studies. The first one is is related to design modification strategies for a Canadian CANDU nuclear power plant and its emergency code calling system. It is important to stress that it is the ECC has special safety system with special requirements and closely monitored with a regulatory body. And as system weaknesses has been discovered, it is the absence of closure of air-operated valve makes that the whole system is lost. So the importance of this problem is that it is a direct violation of fundamental safety principles and defense in that philosophy, where they require that the absence of single point of vulnerability. It means that the failure of one component or one equipment causes the loss of the system. Although the loss of ECC is an analyzed accident scenario in safety report, it represents a major challenge for operators and nuclear safety and could not be tolerated at a permanent basis. So the most challenging bounding scenario is that the ACC is involved in many mitigating actions and accidental sequences, but the bounding case, larger loss of current accident and the loss of ECC at the same time. So in this regard, the Canadian Nuclear Regulatory Body was closely involved, and it is the proper context is that nuclear power plant was 3 years before a major refurbishment. So this situation represented a major asset management making challenge. The first step was to see whether the operators in the control room could control the situation in the case of this failure, and given the time at disposition available, it was not a good scenario. So design modifications were required to install air operating valves in series with existing one. Given special requirements for this system, this process took the qualification took 1 year, 52 weeks. So 3 options were analyzed. The first one is the first option, installation during 6-week specific shutdown planned solely for this modification. So in this case, it was a 1 year time at risk before the installation. The second is during the planned shutdown, which was 2 years from the moment of the analysis. So 2 years time at risk and 2 to 3 weeks on critical part of our normal outage. And the option 3 was to 3 years during the refurbishment, so 3 years time at risk. What is important to stress that there are many uncertainties in play, and the involvement of qualitative and quantitative factors. So engineering works, testing, procurement costed about $7 million without cost of power generation, and it is about 1 million per day on the critical part. So application of this risk-informed model was used to recommend the solution. What is important to say that the respect of safety limits or objectives is 1 10⁻⁴ year per year for severe core damage, and 1 10⁻⁵ year per year larger release frequency was verified through probabilistic risk assessment. In nuclear power industry, the PRA a sophisticated risk evaluation technique and consists on comprehensive integration and assessment of safety or risk of nuclear reactor facility. A short representation, we have a series of initiating events, and through a combination of event trees, fault trees, and other analysis, we calculate core damage frequency, which is the input for the level 2, where we consider the containment performance, and the level 3, which is not regulatory mandatory, considers the impact of the population. In this risk-informed decision-making process, following participants: lead analyst, risk and reliability engineers. It was I was in charge. Decision-making was chief nuclear officer, subject matter experts, operations, shift supervisor and first operator of control room, maintenance engineer, nuclear safety 4 people, reliability people 3 members, engineering 2 members, stakeholders, plant management, and nuclear regulatory body. What is important to stress here that through the probabilistic risk assessment, we considered calculated the value of severe core damage frequency and large release frequency with and without installed air operating valve. And what is interesting is that even without those valves installed, we were below the required limits, so that the gain in nuclear safety, in safety, was quite low, but we were obligated to install those because of respect of regulatory requirements and the philosophy of defense in depth, where the single point of vulnerability has to be absent. So it is the difference between risk-informed decision-making and risk-based decision-making. So even a so powerful technique as PRA was unable to demonstrate the compliance to the high industry standards. So the overall decision-making process took a multi-attribute decision-making approach where the problem safety objectives were considered here. And at the end of the day, the option 3 was recommended, and the decision maker made this decision to recommend that the cost-benefit analysis was performed too. The option 3 was retained, and regulatory body endorsed the solution, and those valves were installed 3 years later. And the second case study is the application of this risk-informed decision-making to the design of electrical power grid. It is the case of a strategic 735 to 315 kilowatt strategic substation with 2 redundant 1.65 gigawatt power transformers, provides electric power to large area residential industrial hospitals. A potential issue was loss of redundancy on function N-1 configuration with economic and social consequences. One of the options was to install a third power transformer. So it is the configuration, and we modeled the substation through dynamic reliability by 2 power transformers, 1 755 circuit breaker and 2 350 circuit breakers, current transformers, and so on and so on. Involved people, risk and reliability experts, and subject matter experts, grid planning and development, 2 engineers, reliability analyst, 2 reliability engineers, operation, 1 power grid operation engineer, and decision maker was a senior level manager. 4 options, status quo: install a double high voltage circuit breakers and auxiliary equipment, another unit for a 3-phase unit transformer, and install a third power transformer. That is the overall model with a combination of reliability block diagram and fault tree analysis dynamic with relevant databases, all that using a discrete event simulation and Monte Carlo simulation. And the analysis was performed at 2 levels. The first level was over a period of 40 years, that includes planned maintenance activities, inspections, and so on. But still, the metrics used was total unavailability over 40 years, and in hours, in percentage, and it is also expected, the simulation provided expected number of system failures over a period of 40 years. So we see that 3 power, installing a third power transformer only reduced 38 hours over a 40 period of time. The second type of analysis was to perform the reliability analysis and degrade the N-1 configuration for various ages of equipment. Given that aging is a quite important factor, we use the variable distribution. And we see that for attending 1% of risk or unreliability, we have various delays or time at our disposition. So the overall decision-making structure includes benefit costs because installing a third power plant required the investment of 33 million plus operating and maintenance cost over 40 years. It's at least 10 million more. It is also a loss of load, image, and then the social impact and so on. And for all those four options were considered. For the time being, the status quo is retained option. In concluding remarks is that I could say that in a complex world exposed to huge uncertainties and risk, resilience and asset management should be connected and integrated and provide a meaningful framework for the decision making and performance and balancing performance, risks and costs. It is also important to stress that top management hold the key to successful asset management because people can break or make the system and break down silo mentality. Asset management major challenge, how to integrate new technologies, materials, scientific knowledge, artificial intelligence, all those smart things with existing ones. Should focus on total business impact, and research and development and innovation are essential. Some of my talks on the potential of using risk-informed decision-making in dam safety. Safety is an important factor, but is one among numerous competing influence factors. High-quality engineering analyses are necessary, but not sufficient for an adequate decision-making. It is the difference between risk-based and risk-informed decision-making. Organization is hard to balance between competing factors, risk, safety, performance, cost, opportunities, long-term versus short-term goals for maximizing value from assets, and intangibles may sometimes be dominant in decision making. In such a context, I think that risk-informed decision-making with a holistic risk asset management and resilience framework could be a sound basis for a good decision-making. So, in dam safety, it is the same. The safety is not isolated from other influence factors, and the holistic approach is probably the best way of performing that. So in this regard, you could, if you are interested, consult some of our papers publication in risk-informed decision-making, and I thank you very much for your attention, and I am honored to be invited to present at this event.
Thank you very much. It's really interesting to see your presentation in the context of the energy and the power systems industry, how it translates so nicely into dam safety as well. Particularly poignant right now with all of the resiliency issues and failures going on in Texas and other parts of the country, given the extreme winter weather they're facing. And it's curious to know what decisions were made in their asset management strategies that might have led to that. We have one question from the audience right now, asking if you could clarify a little bit on the difference between risk-based and risk-informed decision-making. I think that distinction is important, but there's some perhaps confusion or needing for a little bit more in-depth conversation on the differences between the two.
In my understanding, a risk-based decision-making, you develop various models, and by using those models, you get the result. You do get numbers, you get values. And your decision-making is based solely of those results. A risk-informed decision-making takes into consideration other often intangible factors like public perception, regulatory compliance, and so on. In fact, risk-informed decision-making integrates risk-based decision-making. It is the part of, as in the case of emergency call calling system, where through using this probabilistic risk assessment, we demonstrated that we are below safety limits, severe core damage frequency and large release frequency. But despite this fact, we were forced to install those valves because of non-respect of single point of vulnerability requirement. So if the decision-making was based uniquely on the PRA results, we were not forced to do that. But taking into account other factors, we have done that. So if there is any other questions, I will be able to take part in this panel at the end of the day, so we could discuss further those issues.
We have got, again, we're running a few minutes ahead of time, but not anything that's too extreme. It appears that Jason Schneider from Reclamation is set up for presenting right now, so we can move into his discussion about risk-informed design. Jason, if you've got your mic and everything ready, we can give you a mic check. But beyond that, you are free to start. And once Jason has wrapped up with his presentation, just for everybody to plan ahead, we'll have a short break and then reconvene for our panel discussion to close out this National Dam Safety Program Technical Seminar for 2021. All right, Jason, the floor is yours.
All right, thank you. Good afternoon, everyone. So I'll attempt to outline in a very general sense risk-informed design, the way it's being used in reclamation. Another way you can think of it is basically deterministic design with risk-informed decision-making. So first, I'd like to set the stage a little with discussion of the first three bullets here for some background, but I'll try to focus discussion on the fourth item, and that's how do we use risk in design. Being that this is the last presentation, you probably are very, very familiar with these terms already, but just to cover the basics, how does reclamation define risk? It's essentially those two metrics there, annualized failure probability and annualized life loss. Reclamation defines annualized failure probability as the product of a probability of a load and the probability of a potential failure mode. And what's a potential failure mode? Simply, it's just a physically plausible way for a dam failure to develop from existing inadequacy or defects. And the annualized life loss is the product of the annualized failure probability and life loss that is expected from the identified dam failure condition. The risk in terms of AFP and AO can be evaluated against established dam safety guidelines shown on the graph with the dashed gray lines. The goal being to have our facilities risk rank below the AFP and AL guidelines. This concept is easy to visualize graphically with the FN diagram, which I'm sure you've all seen quite a bit. Ideally, we'd like to see our facilities with risk markers and the total risk, shown as the large yellow dot there, to be below guidelines, so below those gray dashed lines. How long has risk-informed decision-making been practiced? Prior to failure of Teton Dam in 1976, within reclamation, dam safety issues were addressed through the periodic examination and project-specific requests for funding to make necessary modifications to dams. But the failure of Teton Dam demonstrated a need for a more comprehensive approach to evaluating and addressing dam safety issues. Thus, the 1978 Safety of Dams Act and reclamation really picked up with the quantitative risk analysis in the 1990s. What structures does risk-informed design and risk decision-making apply to? Essentially, any existing and new risk-contributing facility. Reclamation personally is responsible for 360 plus dams and dikes that can be categorized as high or significant hazard. Typically, structures that are evaluated are embankment and concrete dams, spillways, outlet works, and power plants under our risk evaluation and risk-informed design process. Here, I start to focus the presentation on risk-informed design and how is risk used in design. Essentially, it's a process, and it can be an iterative one, but there are 4 primary steps that I've boiled it down to. The first being identification of potential failure modes. The second, the design effort. The third is risk evaluation, and the fourth is the decision process. The 4 steps are simply shown here in a flow chart for new and existing dams. These are probably fairly difficult to see, but the primary focus I wanted to point out is that there are points in the design and risk evaluation process. Typically at step 4, which I call the decision process, that can cause us to have to circle back to adjust a design that might meet our design standards, but might not provide adequate risk reduction. And so, I'm not sure if you can see my mouse, but there's a couple loop backs here at the decision process, real simply. So step 1, identifying potential failure modes. And my discussion is more focused on existing facilities for simplicity, but this step is typically already taken care of within reclamation, having not constructed many new facilities for quite some time. So we typically have background information from design and construction that have provided us the ability to have at least one, but likely several comprehensive review cycles completed for each of our facilities. In those reviews, we may have determined the need for further study or pursue data collection or potentially enter corrective action. based on aging infrastructure or no understanding of loadings that could impact the structure negatively. This step gets us into the phase of needing to design a modification, and that design needs to meet our design standards and also strive to reduce that related risk to a condition below our guidelines if possible. Step 2, after we've identified the need to come up with alternatives for reducing risk, we look at design. One of the first stages in design is understanding loadings. It's important to have an up-to-date set of loading conditions for the facility. No surprise here on the general loadings we use for design uncertain. What I'll point out here is that our perspective of what the target design load is or should be for design of a new or modified structure has changed over the years and will likely continue to shift. Considering we have facilities that are 100 plus years old, and as we gain more and new ways of understanding loading potential, updating loadings can result in moving facility that might once have thought to be safe to an area of concern. And we experience that within reclamation quite a bit. Another important step of the design is understanding or getting an improved understanding of material properties for our facilities. And what those facilities sit on is critical. Often we're going to pursue a modification and have uncertainties related to our foundations or embankments or concrete dams. We pursue field exploration programs to gain additional and needed information to refine designs and reduce uncertainty. With loadings and material properties dialed in, we can actually design our intended or modified structures to address our dam safety concern. Typically, a deterministic design approach using accepted design standards is used to design a new structure or a modification to a structure. Reclamation has been developing and continues to develop design standards and related chapters for concrete and embankment dams and their pertinent structures. And those are all available, as well as not only do we use our design standards, but we use a lot of other industry design standards related to dam and pertinent structures. Following design, once we have concepts, alternatives designed using our design standards, we should have all the information needed to enter step 3, which is risk evaluation or risk analysis. The level of study and performance of the modifications may vary depending on the complexity of the structure, severity of loading conditions, and potential consequences from failure, but you can kind of get a sense of what we might do for evaluation for our new structure or existing structure and how to modify that. Reclamation uses a team risk analysis approach. The teams consist of subject matter experts for the identified structures and potential failure modes of interest to develop a quantitative risk estimate for the existing, new, and modified structure. Of course, we're interested in the facility portions that we're not modifying and the portions that we are modifying to get a comprehensive understanding of risk. It's important to provide time for the risk analysis team to review any pertinent information related to the design and modifications for the effort that we're going through. And the typical approach for reclamation is to use event trees and estimate probabilities for a series of definable progressive steps that could lead to failure of a structure. using all the information we've developed as part of the investigation and design phase of the project. A simple example would be for, let's say, a reinforced concrete structure, such as a spillway. Information related to the structure's stability in the form of demand to capacity ratios, factors of safety, etc., would be information relied upon during risk analysis to estimate risk. Ultimately, the result of the T-risk analysis is updated estimate of individual and total facility risk with the goal of the design of the new or modified structure to reduce the baseline risk, which originally resulted in the need to develop structural alternatives to reduce risk. Step 4 is the final step in the decision, is basically the final step in the 4-step process I've outlined, and that's the decision process. This is typically where the technical alternatives are presented to the Dam Safety Office. Reclamation has internal review with Dam Safety Advisory Team members who advise the Dam Safety Office regarding adequacy of the design, analysis, and risk evaluation for proposed modifications. Uncertainty is often a key factor in the decision process. Often uncertainty related to loadings, existing structures, their materials, or the foundation may result in further study to reduce uncertainty prior to proceeding with structural modifications. We also have stakeholder and consultant review board evaluations of any major dam safety potential modification that we pursue to reduce risk. So internal and external review to ensure we're above board. This slide provides a visual of the ultimate goal of risk-informed design for our existing high-risk facility, developing appropriately targeted modifications to reduce individual risk contributor and and to bring the total risk below guidelines. And so this is just an example of having a dam with a high baseline risk with several potential failure modes that are above guidelines, and through the risk-informed design process, which I'll repeat can be fairly iterative at some stages, you want to try to reduce risk with those modifications to bring your risk comfortably below guidelines. And comfortably is dependent on the facility, of course, and also the amount of population at risk you have downstream. So it varies from facility to facility. So that's a general approach. I've included an example just to try to explain the approach very simply. So example, Dam A, we have an existing spillway. Maybe it was constructed in the 1940s. When they designed it, and maybe this is generous, they assumed a peak horizontal ground acceleration of 0.1 g. So their concrete and reinforcement was all designed based on that load condition. And recently we've gone through our comprehensive review and maybe issue evaluation and determined that the seismic hazard has increased significantly since original design. And maybe the 0.1 g acceleration can be attributed now to a 1,000-year event. also assume that for this facility, the total risk is dominated by one spillway potential failure mode. Let's say crest wall failure for a gated spillway. Let's say if earthquake hits this structure, there's a high probability of the structure failing. And this would have been determined in our typical comprehensive review or issue evaluation levels. Evaluation of the facility, and with updated loading conditions, we find that we have high risk. And that's confirmed through follow-up studies. And so high risk the risk is determined high enough that we want to consider alternatives to reduce the risk. Because under phase 1, which this would be phase 1, is identify potential failure modes. We've identified that we have an annualized failure probability above guidelines, and with associated life loss, we also have annualized life loss above guidelines. So proceeding past step 1 into step 2, determining or selecting alternatives for modification to reduce risk. We decide one alternative would be to design a new spillway and remove the old. And so our initial target design load for the new spillway would be the 10,000 year event for our design standards. And so that means we'd be using that 10,000 year event of 0.4 G to design our concrete and reinforced concrete element. And through that design effort, we determine the probability of failure for that loading condition per our design is very low, with demand to capacity ratios for shear and moment very simplistically are below 1, which is advantageous. Also for that design, for our design standards, we followed reinforced concrete design requirements for design loads and strength reduction factors. And so that's basically the result of adding some additional factors of safety through code requirements. So step 2 is complete, and we move to step 3, which is risk evaluation. For risk evaluation, typically reclamation will look at a structure under the ultimate capacity condition. And so what we would do is we'd take our design structure, and then for the design event, we would remove our load factors and remove the strength reduction factors and see what our ultimate capacity would be. And as you would expect, our DC ratios would go down, which means our structure's more robust than our design requirements would suggest. And then for risk evaluation, we would look at that structure, its subject performance to higher loading conditions. And so we would evaluate the structure's capacity for the 50,000 year event, 100,000 year event, and whatever other event ranges we might need to, depending on the level of consequences downstream and the level of study that we have developed for the facility. And we would find that perhaps for our target design with the load factors and strength reduction factors considered, when we take those out, we might find that we're in a good situation for the 50,000 year event, but we might start to see a place where for greater than that, we would start to be concerned with potential shear failure or moment failure. And that's how we would develop our event tree probability loading to estimate risk for this modification. So we would take this information into the risk team setting using best practices manual for potential failure mode progression. or using the pre-established potential failure mode progression for the baseline condition, update it for the new structure, and find that based on our target design load and the performance of the structure for the more severe loading, we develop a much lower risk for the modified structure compared to the structure we would like to replace. And so if we see that we've achieved a significant risk reduction and our total risks would be below guidelines, this would be an alternative that we would like to pursue for modification. Of course, there's a process where we would look at multiple different types of alternatives, but for this simple example, let's assume we take this to the Dam Safety Office as our proposal. So we'd step into stage 4, or step 4, which is the decision process. We'd present our results to the Dam Safety Office and the DSAT team, and gain concurrence and agreement with the pursuit of the modification. We would present that the total risks findings for our proposed modification are below guidelines, and determine if they are comfortably below guidelines. There's no set order of magnitude below guidelines based on the variability from facility to facility, but it is definitely a risk-informed decision. And then we would decide to pursue the modification or not pursue the modification, depending on the results. So I'll have an alternate ending here that would change the conditions of our modification and emphasize that iterative loop. So let's say that our life loss downstream for the facility would be 50 instead of 5. And let's say that from the 10 to 50,000 year event, there's a significant increase than what was evaluated previously. Let's say maybe the 50K goes from a 0.7 G to a 1 G, and the 100,000 year goes from a 1.1 G to a 1.5 G. But the 10K is still 0.4, and that might depend on what background seismicity is controlling at your facility. But anyway, we would still design a modified spillway for the target 10,000 year event, and we would evaluate the risk with these higher loading, same loading frequencies, but higher significant loading conditions. And we'd find maybe that our AFP is maybe an order or 1.5 magnitude higher than what it was before the shift. And with the higher life loss downstream, we find that our annualized life loss with the combination of AFP and life loss is above guidelines. And so this would mean that our initial design effort would suggest that we would still be above guidelines in terms of annualized life loss, but not necessarily annualized failure probability. So at the decision point, step 4, there might be a decision to try to target or improve the design such that the annualized life or the annualized failure probability would be lower, such that the resulting annual life loss would not be above guidelines. And so one consideration we could make is go back to the design phase and perhaps design the structure for the baseline condition of the 50,000 year event. And so that might mean that we increase our wall size or add a strut or increase the amount of reinforcement in moment and shear. And that's what this next slide suggests, is that adjusting the design load is not the only solution, and we can consider adding defensive design measures. And so, as I mentioned, we could add struts or anchors or additional moment. or shear reinforcement to try to bring those DC ratios within line so that we have a lower risk profile. Ultimately, the goal is to ensure minimum design standards are achieved and risk is below guidelines. And often, the risk-informed design results in designs that are much more robust than estimated minimum design standards. But I will say that by following our typical design standards, we have a pretty good history of not running into that iterative loop very often. So in summary, how does reclamation define risk? Real simply, annualized failure probability and annualized life loss. And that is our primary metric for weighting risk. How long has risk-informed design been practiced? Well, risk-informed decision-making started in the 1970s, and advancements in methodologies in the 1990s put us into the quantitative risk analysis that we use now. And so quite a while. What does risk-informed design, what structures does it apply to? I would say any risk contributing facility. Reclamation at dams, of course. Anything that could fail that could potentially cause life loss. And how is it being used for design? Essentially just to ensure designs conform to the current state of practice while meeting dam safety criteria. And that's it. Very brief and quick summary of a risk-informed design process for reclamation. I really appreciate your attention and time.
Thanks, Jason, for your presentation. That was a great way to cap off our seminar this year in advance of our panel discussion coming up in a few minutes. I see one question for you. What is the criteria reclamation uses to determine if ALARP has been met?
ALARP is a tricky question to answer. It typically comes in when we're talking about facilities that have extremely high consequence downstream, and it's a case-by-case, facility-by-facility decision, and there's no easy way to answer your question, but I would say it's a big part of the design or the decision process, which I call step 4, to determine if ALARP is met, and yeah, it's just a facility-by-facility decision. Often, ALARP is considered when we're dealing with those high-consequence facilities, and it is a big focus because sometimes you can't bring your risk down low enough when you have tens or hundreds of thousands of people downstream.
As a follow-on, I have a question about, you mentioned your teams of review and multiple levels, and you showed us the FN charts that we've now come to recognize for dam safety. The question I have, as somebody who doesn't necessarily participate in risk work at the state level, is do you ever fold in the public in the risk-informed decision-making? In the sense of, we have tolerable risk criteria, but do you ever kind of calibrate to ensure that what you or reclamation sees as tolerable risk aligns with the person's downstream from the dam and what their risk tolerances are?
That's an excellent question. Reclamation's, I guess, acceptable risk criteria or guidelines are established based on some pretty focused historic failure rates and life loss cases. And I'm probably not the best person to tell you what all those are, but there is consideration of the PR downstream, and reclamation has a lot of situations set up, such as emergency action plans and early warning systems. And if there's a higher risk facility that might not be addressed or modified for years, there's outreach to the community and the local officials downstream if the decision makers determine that there's a need to do that. So it's not typically having the general public weigh in on the results of the risk analysis, but there are considerations of how to make them aware of a situation if we determine there is one.
Great. And Charles Karpowitz chimes in as well about the risk reduction opportunities that exist from that kind of outreach you mentioned. Through, he suggests local meetings, TV channels, newspapers, and the like as ways to implement outreach efforts into risk reduction. So thank you, Charles, for that comment. All right. Well, that.
Okay. Can everybody hear me? Okay. Testing. All right. So we'll get started. So the first question I'm going to ask, and the subject is going to be the ALARP. So we've heard ALARP described, and Eric, I guess I'll ask you this. Eric Halpin, I ask you this question first, and then open it up for some more discussion. So the question is where at in the risk-informed decision-making process does ALARP actually begin? And then what is ALARP? And the second part of that question is what is ALARP's connection?
Can you hear me okay?
Between benefit cost and ALARP.
So the last part I'll tackle first, which is I personally don't think there's a lot of or even any relationship between benefit cost analysis and ALARP. There is a lot of good economics that happen within ALARP, but it's generally not benefit cost analysis. So ALARP generally starts when you're looking at risk reductions that are bringing the risk below the societal and individual risk guidelines. It doesn't have to start there, but that's when it generally starts. And then you measure the degree to which you're justified in taking the ALARP based on things like cost effectiveness as measured through things like cost per statistical life saved. But for some projects, you have exceptional circumstances. So that's when your risk is above societal risk guidelines, and you're still trying to determine are you justified for reducing the risk further as practicable. So that happens with levies quite a bit. And so oftentimes you can have a levy like the city of Dallas, Texas, where it's a 2,000-year levy, and the risk driving failure mode is overtopping of the levy. But there's really nothing practicable that you could do to pull the risk below the societal guidelines. So I would say generally that's where it starts, but it doesn't have to be there. You can apply it above the line. Hey, Preston, it's John France. Could I jump in on that for a minute? Last year, I was asked to chair a group to provide some review of the dam safety risk analysis practices of the Corps, Reclamation, and FERC. That was something that was directed by Congress after the Oroville incident. And we had a 5-member group that I was honored to lead. And we talked quite a bit about ALARP and where ALARP applies, and also relationship to this whole question of tolerable risk guidelines. And a couple of things that we pointed out in the report that I hope is public at some point, it hasn't been yet, is that this question of tolerable risk guidelines, the guidelines that we've been using have really been developed by the agencies in large part, and haven't been vetted through the political process or through the public process. And in the end of the day, we felt okay about that in terms of if they're being used at this point to triage where the greatest risks are and move towards addressing those greatest risks first and trying to get those below tolerable risk guidelines. But as Eric said, once you get below tolerable risk guidelines, we think ALARP is still the overall goal of the dam safety programs. Is to, once you get below tolerable risk guidelines, that doesn't necessarily mean you're done. You perhaps should be asking these ALARP questions of, are there practicable ways to even further reduce risk once you get below guidelines? I'd also agree with Eric that that's not really cost-benefit ratio anymore. That's, can you practicably reduce those risks further, and should you?
And and John, I think you spoke on it a little bit, and I'll give you first crack at this next question to kind of elaborate on it. You spoke in your presentation a little bit about those tolerable risk guidelines, and maybe the agencies, the large federal agencies have an understanding of those tolerable risk guidelines, but where
our panel that put that report together talked about that quite a bit, and tolerable is, it's a question of tolerable to whom, and the agencies, we think, did a good job putting together the guidelines. When they put them together, they looked at some other industries, they looked at tolerability in some other sectors. There's a good rationale behind what they did, but nonetheless, they principally were developed by a couple of agencies, Bureau of Reclamation and the Corps of Engineers, that are self-regulated, and they were, in our view, were agency policies that made sense, but we didn't see, and I don't know in our governmental process how you go through a process of deciding or exploring whether they are tolerable to the public. And is that through Congress? Is it through the political process? Where's the process that we go? I think that's the next step. Do we want to do that? And if we want to do that, how do we do it?
Yeah, this is Eric. I'm on the...
Okay, did anyone else want to chime in there?
Preston, we think that the video is affecting the phone line. Yeah, let's try that, and we might go back into the other room because it wasn't doing this in there.
So cut off all videos? Okay.
But to that point, Des, did you want to make your comment?
Yeah, this is Eric. I was trying to jump in on what John Friend said, but now there's a lot of feedback.
It seems like someone's unmuted, so we're hearing it come through their computer.
Hi, Annie. Can you hear me now?
Yes.
Okay. Yeah, I switched to the phone line. I've had a lot of conversation over the years with John Remington, who is the author of the Tolerability of Risk and Alarm framework that has been essentially adapted around the world. It's adapted in Canada, it's adapted in Australia, and to varying degrees, it's referred to in the various federal agency documents as well. But John was very clear that there is a distinct difference between dams and, for instance, bridges and tunnels, because they are heavy fixed infrastructures that are not readily amenable to modification. And this is unlike other industries, where in fact things are what you would call malleable. And this malleability means that they are amenable to, what I would call, risk reduction over the life cycle of the asset. And malleability by the industries doesn't apply to dams, as I mentioned yesterday, but it does apply to some degree to nuclear power stations, but a very large degree to industry. And there are also a great many contextual issues that must be taken into account before you decide on the numbers. So the actual numbers need to be tailored to whatever suits the type of industry you're talking about. And that's why at BC Hydro, and our interpretation of a LARC is to aim for a very low level of risk at the outset, recognizing that it has to last for many, many decades, and then keep the level of risk as low as we can over the life cycle. Because there's so much gets locked in at design that modifications are exceptionally complicated and expensive. Now, what to do with aging existing infrastructures is a completely different policy question that is not covered in the guidance from the UK Health and Safety Executive on this very complex problem.
Okay, thank you, Deb. The next question is going.
Can I jump in on that one?
Oh, go ahead.
Yeah, hey, this is Eric. So I think there's a bit of a misconception about tolerable risk guidelines and how it gets applied. When the Corps did it, we did 2 international workshops that brought in people that use risk guidelines from all kinds of industries around the world, from legal to transportation to medicine to life safety issues to environmental. And what we found is really that this is not from the perspective of the community, the tolerability, it's from the perspective of the person making the investment. And in the U.S. government, that decision to use the perspective of the agency is backed up by congressional appropriations. So Congress knows how we're making decisions because we brief them on it. And then the Congress makes an appropriation with that view of tolerability in mind from the agency. I think if we think tolerable risk guidelines is about what the community believes is tolerable, then that's not monolithic, and it's not even knowable.
Yeah, this is Sergio. This is Sergio to add to what Eric was saying. That is our biggest challenge in Oroville, where the community or downstream individuals and state and local politicians, they want to dictate or have input on what is considered tolerable. So that is one of our biggest challenge when it comes to this, discussion. So just wanted to add that from a state level, it's at least to date, it's being treated a little different.
Yeah, to add on to this, I'm going to add something from our chat. So John Roach says, with a follow-up from Eric, should states be interested in adapting risk follow federal guidelines for tolerable to create state-specific models? And then we're going to stay on some of the state-specific stuff after this question. So I think that was toward towards you, Eric.
Okay, can you hear me?
Yes.
Yeah, so, that what we're struggling with here is, I think states probably should adopt what others are doing if they're comfortable with the basis of how those tolerable risk guidelines were developed. I mean, the reality in the United States is there is no national dam safety guidelines. There are none. So there's some federal guidelines, and a lot of folks have adopted those to stand up things like safety programs or design inflows or any number of things. If you really want a national guideline on TRG, it will probably never happen. The only thing I can think of that's equivalent to that in the U.S. is the National Fire Code and the requirement for sprinklers in buildings over a certain square footage size. It's just, and it's because we don't have a monolithic country with a monolithic culture and a static set of societal norms. It just doesn't exist.
All right. Well, thank you. So the next question is going to stay on the state and regulator perspective. So this is more directed towards John McCain as well as Doug from FERC, Doug Boyer. I kind of like Doug Boyer, your presentation. You talked about the crawl, walk, run, fly method. And can you kind of tell us a little bit more information on how, and I think Dean talked a little bit about it in his presentation because that was a FERC project as well, between how information is going from the screening level, assessment, all the way up to maybe a qualitative risk assessment. And same thing for you, John. I wanted you just to, I see you're using similar methodologies in South Carolina, and I just kind of want to understand how that information may transfer from that screening level all the way up to further risk assessment. So Doug, if you could start first, and then John, if you could pipe in.
Yeah, Preston, thanks. So we have identified kind of within the FERC program those different levels of risk, and those levels are really tied to decision making and what kinds of decisions we're trying to make at each one of those levels. That kind of introductory level at the portfolio or inventory where we're doing screening of multiple dams to try to get some sense of priority, between the dams, which ones should we start with, versus then the semi-quantitative risk analysis that we saw a number of presentations on, over the week, where now we're starting to look at individual dams and using simplified methods, again, to get some sense of prioritization of activities, of actions, of failure modes for future work efforts versus those quantitative methods, those higher level risk analyses that are more rigorous. And again, that's all scalable within that scheme as well, and actually try to make decisions, on investments or non-investments, from that standpoint. I think we all recognize that within the dam safety community in the United States, there's not a deep pool of talent of folks that we can all reach out to and tap and be able to have these risk analyses done in mass, I'll just say right now. So that's why we're looking at that kind of the concept of, hey, let's crawl first. Let's try out these processes. And again, it's worked quite well for reclamation and the Army Corps of Engineers for many years. There's good precedent, for that within the dam safety industry. The Australians have been using it for quite a few years, and others. So it's not like we're embarking on something that's completely new, but just might be new to us as a tool or a technique to be able to put in our dam safety tool bag. So, but just given that, so we need to kind of generate that comfort level and that confidence within the regulatory bodies, within the consulting community, and with the dam owners in being able to move forward and how we can do that most efficiently and effectively. And so that's going to mean doing some of these pilot studies, at least it was for us to get the confidence and understand what things that we might need to consider as a regulatory agency as compared to, say, what the Corps and Reclamation do as owner and kind of self-regulators on that. And so we've taken this approach for looking at the pilot studies to develop that talent pool and to understand what kind of tools and maybe training would be most helpful, most effective at being able to now start building the bench and getting the depth that we're going to need, what we think we're going to need here in the coming years to actually be able to execute each one of these. So we've got to start out simple. If we make it too complex, I'll just say from my standpoint, my fear would be that we would all come crashing down, because we've tried to do too much too quickly on that, and it might not be perfect at the beginning, and that's got to be okay. I'll just say, at least for us, to be able to go forward. There's concepts and principles that some of us, might not be as familiar with or even brought up in college, understanding from that standpoint. So we need to understand that it's going to take some time to develop that. Some of this is kind of classroom and knowledge base, and some of it, like I mentioned in the talk, we're just going to have to go through and do some of these to understand what some of these concepts really mean and how we actually integrate and implement some of this in a project-specific process and going forward. And then having the reviews of all of those, I think, are going to be particularly important. So we do have that consistency and, again, confidence in being able to make those decisions. And so I just think it'll be a matter of time for us. Again, start out slow, crawl. Once we get more confidence, let's get on our feet and walk and run. And I don't know if maybe flying is too much of an altruistic goal, but that would be nice to think that we could attain that at some point.
Thanks, Doug. And John, a state regulator.
Hey, Preston. I think I don't have a ton to add, but I do want to kind of point out that South Carolina, I guess more from the practical kind of considerations that went into it for us. We were fortunate, I guess, to have already put a lot of the work in place that was needed to kind of embark on on at least a screening level risk analysis for our inventory. We were fortunate that we had already done a very comprehensive inspection effort. Like I said earlier in the presentation, 2,000 dams were inspected in 2017 over a 10-month period. And on top of that, we had already, we had already dealt with a lot of the other dams that weren't included in that 2,000. We had already inspected or put boots on the ground because a lot of those dams were impacted by the 2015 and 2016 hurricanes. So we had a very good baseline of the conditions of our dams, following 2017 to start, or at least to mine kind of that data. And then on top of that, we had done inundation mapping and creation of emergency action plans for virtually all the high and significant hazard dams in the inventory as a separate undertaking. So kind of it's just kind of you know, the stars aligned, I guess you could say, where you know, if we had not had those previous efforts, you know, the cost of undertaking the SLRA would have been much greater. But we really didn't have to do a lot of new work aside from the creation of kind of the framework and just more of the you know, more of the mechanics of how, you know, how we were going to, you know, assign scores and combine, you know, and calculate an overall kind of a risk factor. And so from a practical perspective, you know, we just happened to have everything kind of in place, so it worked out well. We, you know, and we were not able, you know, the big kind of driver was to be eligible for the HHPD grant, or to have dams that we could say are eligible for the grant. So that was also a big driver. But for a long time, we wanted a way, or needed a way, to kind of rank our dams based on, you know, condition, consequences, you know, hazard, you know, whether it's seismic or flooding. So it also gave us a way, you know, that system we've been needing for a while to rank our dams, to help with our decision making, you know, and allocation of resources. So, you know, that's all been. So we are definitely still in the crawl phase. We're not. I don't think we're really even walking yet. But you know, taking it beyond the screening level, we are going to make that. I mean, realistically, that's not something we can't implement that without regulatory changes. So it basically, you know, the semi-quantitative risk analysis or anything beyond that will be for basically a dam to propose, you know, a rehabilitation project under the HHPD grant. So that's where the SLRA, the screening level, is something, you know, we are going to continue and constantly, you know, update those rankings, you know, after every inspection, after every repair, or, you know, anything that can affect the risk score. You know, we will continuously update our screening level rankings, but the anything beyond that, you know, I only really see that being for grant eligibility purposes. So I hope that answers. I hope that's what you. I don't. If there's anything else, just let me know.
Yeah.
If I touched.
You definitely did. Thank you, John, and those answers. I'm going to read a comment from Irfan in the chat. Community acceptance of risk depends on risk perception, which brings in a lot of non-technical issues related to risk communication, models of risk, social amplification or attenuation of risk perception, etc. We see divergent perceptions of risk in communities currently playing out with the COVID pandemic. Thanks for that. Thanks for that comment, Des. Now I'm going. I know you had a comment in there as well, and you had your hand up to give you an opportunity. Des, are you still?
Well, I just wanted to raise the issue of liability and potential for negligence. There were two recent cases but they're outside of the US. But one was in Australia. Can you hear me now?
I can hear you, Des.
I can hear you. Des, I think now we lost you. We could hear you.
Can you hear me now?
I think.
Okay.
Yeah, we can hear you.
The question of liability and negligence is a big question. There was, you know, a case of just flooding in Australia, Ivanhoe Dam, that, you know, brought all sorts of issues into play in relation to acceptability of risk. And there was a case in Ireland which, also, and again without dam failure, that also, raised serious questions around all of this. So the whole question about liability and negligence actually varies across the spectrum. If you're a national dam owner, it's one particular context. If you're a private dam owner, it's different. If you're a state dam owner, it's different again. And it's a very, very awkward, issue to try and deal with, because you can't foresee how any particular judge is going to, actually respond to a particular situation.
All right. Thanks, Des. Moving on to another question. And Joel, I saw your hand up, and I'm going to give you this next question is for you. And so, if you want to address something, I'll give you that opportunity. But the next question I have for you, Joel, and Katie, we did see so maybe differing agencies opinion or maybe definition of cost effectiveness and using benefit cost analysis to either determine our cost effectiveness or the difference between cost effectiveness and benefit cost. And so first, I'm going to have you kind of respond to that, and then after you get through with that, I'm gonna kind of bring it over to Katie Grizzly Brown from FEMA to answer that as well.
Thank you, Preston. I'm just going to make a couple of comments on the previous topic, and I think it's so one of the things I think, as I saw in the chat, kind of related to standard of care. I used to work in private industry, working more in terms of structures, housing. In the Colorado area, we had a time when, because of not knowing all the expensive soils, the standard of care became a requirement to have certain things done, drilling a borehole for each residence before you can construct a house there to understand the consequences. And so I think some of that needs to be considered as just, when we talk about tolerable risk, is what is the standard of care. But in addition to that, we need to also talk about, and I know this is a very sensitive thing to think about in terms of cost for doing these things. Because if we really wanted to bring something to as low as reasonable practicable, we can essentially remove the dam and build a new one. But that's a very expensive cost, and you cannot just do that in any way. So even when we talk about putting in certain standards for federal or local and so on, that is a very challenging thing to do. And so I think it is correct that states should look at it, from a case-by-case basis to see if the federal standard that's there, federal guidelines that are there, are applicable to them. And so then I'm going to jump to your question as far as, I presented cost effectiveness as far as what reclamation does in putting forward projects for modification reports with OMB. And it sounded different from what Katie had presented, and Katie, you can answer this for yourself. But for me, one of the things I see is that we're not necessarily different. It's just that we're using different analysis, which either one, cost-benefit analysis or cost-effectiveness, are outlined in the guidelines as alternatives that we can use. The biggest difference I see is that when we look at cost-effectiveness, we're comparing the cost of the actual alternative we're looking at and the lost benefits from several alternatives that we're looking at, including the structural and non-structural alternatives. Whereas in benefit cost ratio, we're looking at the comparison of what are the costs and what are the benefits. And you have to have, those above the other. The benefits above the cost. Now, that's not to say that in benefit cost ratio, in the cost effectiveness, we're not looking at what the cost is. We do care about how much it costs. It's a matter of, again, going back to the idea of what is the risk that we're looking at? What are the non-quantifiable items that you cannot put on a piece of paper? And I think I mentioned one of the shortcomings of benefit cost analysis
where is it asked to quantify every single thing? Sometimes due to either lack of knowledge, lack of information, you cannot quantify everything. And so it is, I think those are some of the main differences that I see between the two. The guidelines do say you can justify which method you use as far as economic analyses. And so therefore, if you can justify using cost benefit or cost effectiveness, I think you have that option. So maybe I'll let Katie add on to it or correct me.
No, I would say that the cost effectiveness is a requirement of the hazard mitigation assistance grant. And so benefit cost analysis is how the cost effectiveness is demonstrated.
Okay, I think that's a good way to put it because.
Go ahead, Joe.
Sorry, Preston. Yes, because in both instances, you're still looking for cost effectiveness. And so I think Katie summed it up very, very well there.
Hello, Preston. This is Jason. Can I just toss in a couple thoughts on that one?
Definitely, Jason. Go ahead.
I typically think of, when you do a benefit cost analysis, you're trying to show that something is cost effective. But if you do a cost effective analysis, as was discussed in some of the presentations on Wednesday, that you have a common goal, and how do you meet this? What is the most cost effective way to meet a certain goal? When you're doing a benefit cost analysis, you have a without project analysis that you're comparing the benefits and the cost to the impacts compared to a common baseline without project condition. When you're doing a cost effectiveness analysis, you don't have a baseline necessarily. You're really comparing that to a common goal such as a standard that you must meet. And that's kind of the two differences. They do follow a lot of the same principles, but they do have some slight differences in what the outcome is going to be, because you're really in the cost effectiveness, you're trying to reach a certain goal, and what is the best way to reach that. It doesn't necessarily mean that an alternative is cost effective in a cost effective analysis. That's it.
Thank you so much, Jason, for piping in on that. Now we're going to go to some questions that were asked before that we may have not gotten to. So the first question is from Ross from the Corps of Engineers, and he wanted to know. And Sergio, I'm going to give you first shot at this because there's been some back and forth already with you with this one. How are dam owners performing risk-informed decision-making with the presence of various consequence types, i.e. life safety, economic losses, / damages, reputation, environmental, etc.? What are ways to think about the decision-making for life safety risk and those with more financial risk?
Yeah, thank you, Preston. What we did as part of the comprehensive needs assessment, we actually used event trees. And as I mentioned during my presentation, not only did we look at the ultimate failure, but we also looked at heavy damage, light damage, no damage, because as we all know, there are events that are lower in magnitude that could actually have a higher consequence. With respect to the consequences, we looked at life loss or public safety, regulatory compliance, and then given that Oroville Dam and Reservoir is the one of the main purposes is for water delivery as part of the state water project. We looked at the flexibility and reliability for that effort, and we also looked at flexibility and reliability for other purposes that are part of the state water project, and lastly, financial impacts. so as the teams did their analysis, we looked at what were those consequences, or what failure modes that had the highest consequences, and then based on that, we made the decision, or looked at how could we reduce those risks, in particular to the ones that had the highest public safety and or life loss. So that's kind of, we believe we followed what the federal agencies have been doing for the last 30, 40 years. So that's the way we went about it.
All right, thank you, Sergio. The next question I have is for Dean Durkee, and I'm gonna have a follow up for this question from my own, and I want you to start with this question, then I'll have another one right for you, Dean. But any feelings or thoughts about how RIDM is affecting the rate of project failure / incidents?
Yeah, I would say, when you say RIDM, I'm assuming we're talking about FERC rolling out the RIDM process?
You can take it like that.
Or maybe more generally, just the push.
I would think it generally. Yeah.
Okay, so we'll say just generally in terms of moving in that direction. I think it's too soon to tell. I mean, the thought, I think, is, and I think Doug and others on this call could maybe better answer this, but I think we have some confidence that it will reduce to some degree the numbers of incidents and failures that we've seen in the past. But I don't think we've been at it long enough. It's really just developing. If you compare it to, maybe we could compare, maybe Des could talk about Canada. I don't know if somebody's on that would have some perspective on that from Australia.
It's Des. Can you hear me?
Yes.
I would say that, risk-informed decision-making has made things easier for us. Can you hear me now?
Yes.
Yeah. Risk-informed decision-making has made things easier for us over the years, but the important point is that the process that we use, based on vulnerability, we can actually check to see, are we picking up the most prominent weaknesses over a long period of time. So after over 20 years, we've been able to calibrate our process against what we found in our targeted investigations, and it has come together very well insofar as we have reasonable confidence that by working in this structured framework that we are in a defensible position, because the way the various deficiencies that we've rectified line up with the original estimates of their seriousness.
All right, and kind of building on something that Jazz had in his presentation, and it's not a direct quote, but it was a quote from 1981 that it might be possible to develop a subjective rating system, but they were worried that there were not enough experienced engineers that could be able to apply it in a reliable manner. So that was written in 1981. I'm just wanted to understand where is the industry and how are we building up engineers and younger engineers to be able to perform risk analysis in the future. And this is for anybody on the panel. Made everybody quiet.
Could you repeat that? There was some echo.
Okay, so if their lines, so just wondering in the industry, where are we at building up new engineers when the engineers that are currently out there doing risk analysis when they retire or move on to other things, what are we doing as an industry to get the new subject matter experts up to speed and up to par to keep this type of analysis going and actually getting stronger?
Preston, this is Dean. Can you hear me? Can you hear me okay?
Yeah, I can hear you fine.
Yeah, so maybe I'll take a shot at that. You raise a really important point. I think we can safely say at this point, and Doug talked about this earlier, that as an industry, particularly maybe in the U.S. and many other parts of the world, we are behind, and we have to do two things. One is develop more training that is open to all of the industry, and the other is whenever we're involved in these types of workshops, and I've seen this developing in many of the workshops that I've been involved in, is that we're bringing younger folks with us to the workshop, finding a role for them so they're introduced to it right away. They, like, maybe some of the folks on this call were introduced to risk early in their career, but I would venture to guess that most of us weren't. And it became something that we had to learn later on. And I think that the younger engineers are going to benefit significantly from their involvement in risk, in workshops, and in a risk approach to things very early in their career. And that could ultimately extend even into the academic experience. So that would be my perspective on it. I think it's happening sporadically, but there is a need for instance, support on a facilitation team, and there's always something for folks to do. And Sergio, I think you probably saw this quite a bit in all of the work that you guys were doing at DWR. There's a team of people involved, and many of them are pretty young and inexperienced, but they're learning it from the ground up. And of course the training, USSD is offering training, ASPSO is starting to offer some of this training, and Reclamation in the Corps are trying to make this available.
Yeah, Dean, this is Sergio. From a department perspective, RITM is something that's new to us. We, as part of the legislation mandate, we brought in experts in this arena, and not only did we have subject matter experts, but we also had a lot of young DWR personnel during these workshops, so that they could start getting exposed to this process. Additionally, as part of the CNA project, we had a number of young engineers involved through that process, and the department has conducted additional RITM workshops for some of the other facilities that the department owns and operates. So the department is making a huge investment, but I think in the long run we would greatly benefit from that investment.
Preston, can I add on to that? This is Rachel. I think what Dean mentioned in terms of bringing up young folks, and I can probably safely say I'm still in that category, that firsthand experience with risk and just getting comfortable with the nomenclature, getting comfortable with the concepts is really important. We still see that there's people with 20, 30 years of experience that until they become comfortable with the risk concepts, it is challenging to plug even very seasoned, very experienced, very knowledgeable folks into a risk analysis setting and have them feel comfortable in how they're calibrated. Des has talked a lot about their sort of internal validation and calibration of their risk results. And so I think that opportunity, the earlier you can get exposure to risk and really understand what's going into each step of that process, the easier and quicker you obtain that calibration to really help you become a leader in the next project.
Thank you. I really appreciate that. Now, I'm not sure if David Bowles is on the line or not, but if David's not on, maybe somebody else can pick up this question.
I am. I'm here.
Okay, great, David. David, yep. you mentioned in your presentation that in dam safety, the undesirable event was defined as a dam failure. Now, when speaking on the risk in context of dam safety, we commonly speak on the risk of dam failure or uncontrolled releases of a reservoir. My question is this: when you're looking at non-breach risk, such as an operational release of a reservoir, some of the same consequences may happen because of that release. That may have happened during an uncontrolled. It's just a controlled release. Now, do you think is risk-informed decision making? Could it move towards including some of those additional non-breach risks like that? What's your thoughts there?
Yeah, that's an interesting question. So I think the quick answer is yes, because as you point out, some of the considerations have some similarity, in terms of the types of consequences. But I think it's important to keep the two separate, and the reason for that is that when you're considering dam failure risk, and by the way, I don't limit that to uncontrolled release. It can be some kind of a damaged state as well, as has been discussed by others. So when we're dealing with the failure aspect, then it's important that we're understanding what component of the risk there is driven by failure. So in other words, if you're including the non-breach operational risk in your concept of the risk, that non-breach operational part is not reducible by making the dam safer. It's driven by the way the dam is operated. So it's important to keep them separate. And there's also issues that go along with how you evaluate the non-breach risk versus the failure risk. Our work in trying to sort of develop tolerable guidelines has focused on the idea of the failure.
so I think we need to keep them separate from that standpoint of understanding them, from the standpoint of understanding what the options are for reducing them, and also that the way we evaluate them might be different as well.
Thank you very much, David. The next question, what we're going to do is we're going to move back to some of the FEMA benefit cost analysis questions. We got a lot of questions, especially on Wednesday about FEMA benefit cost. Katie, could you describe a little bit about our discount rates, and then and I think some other agencies had different discount rates, and where they got some discount rates from some of the other agencies as well. You can jump in.
The discount rate for the Federal Mitigation Project is set by the Office of Management, the OMB. So that's where the 7%, that's where we receive that information from OMB, and we use 7%. And 7% is actually set in the program, so you don't have to go in and enter in the discount rate. The Benefit Cost Analysis Toolkit does those calculations.
Oh, okay, and Joel, I'm not sure if it was the Bureau of Reclamation that was using another rate or not.
That is correct. Bureau of Reclamation uses a different rate, and actually this year, for 2021, the rate is 2.5%. And I tried to kind of gather a little bit more information on what the differences are and where does it apply. And the best I could find is that, you know, based on public law, that's what Reclamation has been given the authority to use. It's still through the OMB. We have been given those opportunities to use that lower rate. Now, when we present our information to OMB, they will still ask us to present both the 7% and the 2.5% rates of what those costs are going to be. And then, so we calculate those both, but typically we're using the 2.5% in our calculations.
Okay, thank you, Joel. And going back to a discussion that we had a lot of discussion in the chat over, and I'm not sure if David Bowles, during your presentation, if you got to look at all those chat questions, but that discussion was about using population at risk to determine your risk assessments instead of life versus life loss. Would you care to kind of comment on that a little bit, David?
Yeah, happy to do that. Thank you. Yeah, it's an important question, and as I think was mentioned in at least one of the questions, when we start out, it's the entire population at risk that is threatened and that needs to be evacuated in the event of a potential dam failure. So that's certainly the place to start. But I think there is an important difference between working with and focusing on the population at risk versus the potential life loss. Here's a quick sort of extreme example. Suppose you've got a population at risk of 100,000 people, and the circumstances are such that you can evacuate 100% of them. And then you've got another population at risk of 10, and the circumstances there are such that you can't evacuate any of them. So there's a significant difference there between 100,000 and 10 for the population at risk. But there's also an important difference between the
potential to evacuate everybody in the first case and nobody in the second case. Now, so it's very important to make that distinction, but it's not just about numbers, it's really about understanding. There's tremendous insights that come, particularly using a simulation approach to try and estimate life loss in terms of where there might be bottlenecks in evacuating people, where there's people in the community that might be hard to reach with messaging, and so on. And this understanding also leads to the identification of opportunities for potentially improving the effectiveness of evacuation and warning systems. It's not perfect, but it does provide some very good, very helpful insights. If you go about it in a way where you're trying to understand what would happen in the event of a dam emergency. So there's a major difference there between PAR and potential life loss, and it's important, I think, in our risk analyses to make that distinction and to recognize that that the potential magnitude of life loss is what we're trying to avoid, but it's also what is, you might say, motivating and justifying the extent of risk reduction as well.
Thank you, David. My next question, and we only got about a couple minutes left. We'll go to John France real quickly. I know you spoke a little bit about your presentation on the system that U.S. Fish and Wildlife Service was doing. How might a state kind of use a similar type of system, or what's your thoughts there?
Sure, Preston, thanks. Yeah, actually, there are two states that I know of that are using an adapted version of that Fish and Wildlife system. Colorado and New Mexico both have taken something fairly similar and adapted that, and they are now going through their portfolios as they have resources available to do screening level risk assessments on them. And they've tweaked it a little bit, but I think that system is a good starting place. Colorado actually, in their system, put together templates for failure modes to be considered, not exclusive of other ones you could add, but at least as a base list of a fairly large number of failure modes to consider in the risk analysis. And they're constructed in, if you where they have failure modes event by event with blanks where you can fill in specifics on them, and they're having a pretty good bit of success with that. And I think they're also are having owners who are finding the process to be helpful to them and learning more about their dams. So there are a couple of good models out there. Colorado's actually written a couple of ASDSO papers on how they've applied that, and would be a good place for states to have a look at as a way to take that system from Fish and Wildlife and adapt it to state use.
Thank you, John. And with that, I think we're out of time. I do want to thank everybody, because I think this has been a really good technical seminar. I don't think this discussion needs to stop here. I do know that there are some other trainings that are going to be going on from different organizations about this, and I think that there needs to be more facilitated discussion on this, because this is a topic that I think is getting large, getting real large, and there's a need for us all to really understand risk assessment, as well as benefit, cost, and ALARP, and all the other things that really come along with it to help us make those good decisions. Whether you're a consultant, whether you're
dam owner operator, whether you're a federal entity. I think we all have a real stake in this game, and definitely we're happy as the National Dam Safety Program that we were able to put on a seminar to discuss that this year. Now, saying that, I do want to thank all of our presenters this year. I think you did an excellent job. I think that you're second to none. I thank the panelists for staying for a little while to answer some of the questions. So presenters, just so you know, we did not get all the questions answered. So we will definitely be reaching out to you all to help us to answer some of those questions that were asked that were specific to your presentation, and get that out for the greater group for their needs. Last but definitely not least, I want to thank every member of our task group. And Alicia, do you have the members of the task group slide for us? Because I want to thank all of them by name, because they really did a good job. They really did a good job. We'll start with our facilitators that facilitated each day. So we had Jim Gallagher from New Hampshire. He did an excellent job on Wednesday to present, as well as Joe Malama. He actually presented with us. He was our facilitator on Thursday, and he's from the Bureau of Reclamation, and as well as John Roach from the state of Maryland, who did an excellent job today to present. We do have some people working behind the scenes. The person who got all these questions together was Danny Rodriguez from the United States Army of Corps of Engineers. We have Liz from the Federal Energy Regulatory Commission actually helped as well. Katie Goolsby Brown, who you heard speak, and she was our first presenter, and she's our first presenter to sign up, as well as Francisco. He got most of you to present today, so thank you for Francisco for helping in this particular seminar. I know I probably left someone out. I was hoping to have it in front of me, so I wouldn't do that, but that's okay. If I left you out, sorry. But thank all that committee. Now, I think all has been said and done. We do owe you some information. Please send us in the information about the evaluations and about what technical seminars that you might want to see and hear next year. We do take those into consideration. We want to get better. We want to get better every year. Maybe next year we'll be all together back in EMI and have some virtual capabilities as well. So those are some things that we can definitely think about. We did like the numbers that we got this year, and we want to make sure that we have get this out to everybody. So when you get that email from Paul Gannon or someone from James Blazes from EMI, you know that's for you to kind of sign up for this technical seminar and sign up for it next year, and come and definitely come to EMI if you can, if that's open again. So saying that, thanks everybody so much, and talk to you next time. All right. Goodbye. Bye-bye.
Bye, and thank you.